Hello there, and welcome to Science for Sleep, where curiosity is allowed to stay awake for a little while, even if the rest of you would rather not. Tonight, we're going to spend some time among stars. Not individual stars, at least not for very long, because stars have a habit of gathering together. Some form small, loose groups that gradually drift apart. Others collect into enormous crowded systems containing hundreds of thousands, sometimes millions of stars. Some are so young that they are still surrounded by the gas and dust from which they formed. Others are so old that they were already ancient long before our sun existed. These are star clusters, and over the course of our journey, we're going to look at the different kinds astronomers find across the universe, from young stellar groups that have barely emerged from their birth clouds to dense globular clusters that have survived for billions of years. And before we go any farther, take a moment to look around wherever you happen to be listening. Perhaps you're in bed with the lights already off. Perhaps you're on a sofa, promising yourself that you'll move to bed eventually. Maybe you're somewhere on the other side of the world, listening during an afternoon that is behaving suspiciously like someone else's midnight. Where are you listening from tonight? And if you could see the sky clearly from where you are, do you know which stars would be above you? It's quite possible that some of the points of light visible from your part of Earth belong to stellar families much larger than they first appear. A few stars that seem unrelated from the ground may have formed together. Others that look close together may have almost nothing to do with one another and simply happen to line up from our point of view. Astronomy does enjoy making introductions complicated. If you find these slow journeys through science useful for relaxing, sleeping, or simply learning something without anyone suddenly shouting at you about a shocking discovery, you can leave the video a like and subscribe to Science for Sleep. It helps more people find this quiet part of the internet, and it lets us keep wandering through subjects that probably deserved more than the hurried paragraph they received in a school textbook. For now, settle in, let the day become slightly less important, and let's begin with a question that sounds easier than it actually is. What makes a star cluster a star cluster? At first glance, the answer seems obvious. A star cluster is a group of stars. Unfortunately, astronomers are not permitted to leave things that simple. Look toward a crowded part of the Milky Way, and you may see thousands of stars packed into a small area of the sky. That does not necessarily mean those stars form a cluster. Some may be a few hundred light years away. Others may be thousands of light years farther behind them. From Earth, they happen to appear in the same direction, rather like people standing in a long queue when viewed from the front. They may look close together without being close together at all. A genuine stellar group usually has something more important connecting its members. The stars tend to share an origin. Stars form inside enormous clouds of cold gas and dust, particularly molecular clouds containing large amounts of hydrogen. These clouds are not perfectly smooth. They contain denser regions, filaments, knots, and compressed pockets of material. In places where enough matter accumulates, gravity begins pulling the material inward. One collapsing region can produce a star, but large star-forming clouds often produce many stars during the same general episode. Instead of a single star appearing alone in space, dozens, hundreds, thousands, or sometimes far more stars can emerge from related material. So most stars begin their lives with company. That company can be rather crowded. A newly forming group may contain bright, massive stars, small, cool stars, stars similar to the Sun, binary systems, and objects so young that they have not yet finished contracting into stable main sequence stars. They may be surrounded by thick gas and dust, making the whole region difficult to see in ordinary visible light. There is also no requirement that every member of the group be identical, quite the opposite. A single star-forming region can produce stars with a broad range of masses. Some stars may contain many times the mass of the Sun and live only a few million years. Others may be faint red dwarfs capable of surviving for periods far longer than the universe has existed so far. What connects them is not that they look alike. It is that they came from the same general stellar nursery and formed at roughly related times. That gives astronomers one of their first clues when trying to decide whether a group of stars belongs together. Age. Suppose you observe several hundred stars occupying the same region of space. If one appears extremely young, while another seems several billion years older, that would make the idea of a single shared origin rather awkward. A proper stellar group usually shows evidence that many of its members formed during the same broad period, although real clusters can be more complicated than the simplest textbook picture. Some massive clusters show evidence of multiple stellar populations, and the exact history of how those populations formed is an active area of research. Nature occasionally reads our classification systems and decides not to cooperate. Still, shared age remains enormously useful. Astronomers can estimate the ages of stars by examining characteristics such as their brightness, temperature, composition, and stage of stellar evolution. When many stars in a cluster are plotted on something called a color magnitude diagram, patterns begin to appear. A color magnitude diagram is essentially a way of organizing stars according to their brightness and color, which is closely related to surface temperature. Hotter stars tend to appear bluer, cooler stars tend to appear redder. For a group of stars born at approximately the same time, this diagram can act rather like a family photograph in which everyone is aging at different rates. Massive stars evolve quickly, smaller stars evolve much more slowly. If the most massive stars that could once have existed in a cluster have already left the main sequence, expanded into giants, or ended their lives entirely, astronomers can use that information to estimate how long the group has been around. This is one reason star clusters are so valuable to stellar astronomy. If you study isolated stars scattered around a galaxy, their ages can be difficult to determine. But in a cluster, you have a population that often shares several important properties while containing stars of different masses. It becomes a natural laboratory for watching stellar evolution at different speeds. There is another clue hiding inside the stars themselves: their chemistry. A star preserves information about the material from which it formed. Astronomers can split starlight into a spectrum and use the resulting pattern of absorption lines to identify chemical elements in the star's atmosphere. Hydrogen dominates most stars, with helium close behind, but astronomers also measure heavier elements. In astronomy, rather confusingly, almost everything heavier than helium may be referred to as a metal. Carbon is a metal, oxygen is a metal, iron is obviously a metal which must be a relief to iron. Stars born from the same cloud tend to begin with broadly similar chemical compositions. This means chemistry can sometimes provide another clue that apparently separated stars once belonged to the same formation event. Astronomers occasionally use the phrase chemical tagging for the larger idea that groups of stars may carry chemical signatures of their birthplace. It is a difficult technique because the Milky Way has been mixing stars for billions of years, and different clouds can produce stars with similar compositions. But combined with other evidence, chemistry can help reconstruct stellar relationships that are no longer obvious from appearance alone. Then there is motion. This is one of the most useful clues of all. A group of stars may spread across a surprisingly large region, but if its members are moving through the galaxy in similar directions and at similar speeds, that shared motion can reveal a common history. Imagine releasing a handful of tiny beads onto a gently moving surface. At first, they may be tightly grouped. Later, they spread apart. Even after the group becomes difficult to recognize by position alone, the beads may continue traveling in broadly similar directions. Stars can behave in a related way. A young cluster may begin as a recognizable concentration. Over time, interactions among its stars and gravitational influences from the surrounding galaxy can loosen the group. Stars escape. The cluster stretches. Eventually, its former members may become mixed into the general stellar population of the galaxy. Yet for some time, their motion can preserve evidence that they once belonged together. This has become particularly important in our own galaxy, because astronomers can now measure stellar positions and motions with extraordinary precision. The European Space Agency's Gaia mission has mapped the positions, distances, brightness, colours and movements of enormous numbers of stars throughout the Milky Way. Instead of looking at a patch of sky and asking which points merely appear close together, astronomers can examine how stars are distributed in three-dimensional space and how they are travelling through it. A group that looks unimpressive in a photograph may suddenly become obvious when its stars all reveal similar motion. It is a little like watching commuters in a railway station. From one photograph, you might see hundreds of people mixed together and have no idea which of them are travelling as a group. But if you could track everyone's position, speed, direction, starting point, and perhaps inspect their luggage for suspiciously matching holiday hats, the relationships would become easier to identify. For stars, Gaia provides part of that tracking information. Still, shared origin, shared motion lead us toward another issue, and this is where the definition of a cluster becomes slightly less comfortable. Gravity. Many star clusters are gravitationally bound systems. That means the stars are not merely passing through the same neighbourhood. Their mutual gravity helps hold the group together. Every star pulls gravitationally on every other star. In a cluster containing hundreds of thousands of stars, all those gravitational interactions combine into a complicated system in which stars move around the cluster's common centre of mass. They do not sit still. A photograph of a globular cluster can make it look almost permanent, as though someone scattered stars into a ball and then carefully asked everyone not to move. In reality, the stars are in motion. They orbit through the cluster. They pass one another. Their gravitational interactions alter their paths. Some move inward, others outward, and occasionally a star gains enough speed to escape from the cluster entirely. Whether a stellar group remains together depends partly on the balance between its gravity and the motions of its members. If the system contains enough mass in a sufficiently compact region, its gravity can keep most of the stars together for a very long time. If the group is loose, stars can escape more easily. The surrounding galaxy also interferes. A cluster orbiting within the Milky Way does not exist in isolation. It feels the gravitational field of the galaxy. It may pass near giant molecular clouds. It may move through the galactic disk. Other massive structures can disturb the orbits of its stars. Each disturbance can remove a little stability. Over millions or billions of years, depending on the cluster, those effects matter. This gives different star clusters very different lifetimes. Some stellar groups are temporary arrangements on astronomical scales. They form, remain recognizable for a while, and gradually lose their members to the galaxy. Others are remarkably durable. Globular clusters, for example, can survive for billions of years. They're generally much denser and more massive than ordinary open clusters, and many contain some of the oldest known stars in their galaxies. An open cluster is usually less dramatic. It may contain tens, hundreds, or thousands of stars in a comparatively loose structure. Its stars can gradually disperse through gravitational interactions and disturbances from the galaxy around them. Neither type is better at being a cluster. One is simply much more committed to keeping the group chat alive. The distinction also becomes fuzzy when we look at stellar associations. An association contains stars with a shared origin and shared motion, but the stars can be so widely separated that the group is no longer gravitationally bound. Its members are moving apart. Astronomers still study associations alongside star clusters because they preserve important information about star formation, particularly very recent star formation. Some contain massive O and B-type stars, which have short lives and therefore cannot have travelled extremely far from where they formed. Finding these stars moving together can reveal a young stellar population, even when there is no compact cluster left to photograph. So already our original question has acquired an inconvenient answer. What makes a star cluster a star cluster? It depends slightly on what kind of stellar group we're talking about and what stage of its life we are observing. A useful starting point is that cluster members share a physical relationship rather than merely appearing near one another in the sky. They commonly share an origin. similar ages, related motion, and often a gravitational connection, although some related stellar populations have already become unbound. That definition matters because the universe produces stellar groups across an enormous range of sizes and densities. At one end, you can have relatively small open clusters with only a modest number of stars. At another, a globular cluster may contain hundreds of thousands or millions. Young massive clusters can pack large numbers of hot, luminous stars into surprisingly compact regions. Nuclear star clusters occupy the central regions of galaxies where stellar densities can become extreme. Other systems sit awkwardly between familiar categories, forcing astronomers to ask whether they are unusually large star clusters, unusually small galaxies, or objects with histories complicated enough that the label depends on whom you ask before coffee. The terms we use are descriptions of nature, not instructions that nature has agreed to follow. A cluster also changes throughout its life. When it first forms, it can still be mixed with the gas that produced its stars. That gas matters. Imagine a young collection of stars embedded inside a molecular cloud. The stars contribute gravity, but so does the remaining gas. Then massive newborn stars begin changing their surroundings. They produce intense ultraviolet radiation. They create stellar winds. Eventually, the most massive members may explode as supernovae. The remaining gas can be heated, pushed away, or expelled from the region. When that happens, the gravitational environment of the young stellar group changes. A collection that seemed comfortably held together while surrounded by large amounts of gas may find itself with less mass contributing to the system's gravity. If the stars are moving quickly enough, some will escape. In certain young groups, many may escape. This early period can help determine whether the newborn population becomes a long-lived cluster or spreads into a looser association. After that, the surviving cluster continues evolving internally. Stars repeatedly pass through the cluster, exchanging small amounts of energy through gravitational interactions. Over long periods, this process can gradually rearrange the system. More massive stars tend to become concentrated closer to the centre, while lower mass stars can migrate toward the outskirts. This effect is known as mass segregation. The cluster may also lose stars through evaporation, a term which sounds as though stars are gently turning into vapour, but thankfully means something less alarming. Repeated gravitational encounters can give certain stars enough energy to escape. One star departs, then another, then another. The process may be slow, but astronomical systems are rarely short of time. External gravitational forces can speed things up. As a cluster travels around its galaxy, the galaxy's tidal field can pull at it. Stars near the outer regions are especially vulnerable. Over time, escaped stars may form long stellar streams extending along the cluster's orbit. In some cases, astronomers can observe these streams and effectively watch the evidence of a cluster being dismantled by its host galaxy. This means the boundary of a cluster is not always obvious. There may be a dense core of stars that are clearly members, an outer region containing stars still weakly attached to the system, and extended structures of former members that have recently escaped. Ask where exactly the cluster stops, and nature may respond by slowly removing the border while you're trying to measure it. Astronomers therefore combine several kinds of information. Where is the star? How far away is it? How is it moving across the sky? How quickly is it moving toward or away from us? How old does it appear to be? What is its chemical composition? Does it follow the same pattern of stellar evolution as the other suspected members? Does its motion make sense within the gravitational system? A star that satisfies several of these tests can be assigned a high probability of membership, and membership matters enormously. Suppose you're trying to determine the age of a cluster and accidentally include unrelated stars lying in front of or behind it. Your stellar family portrait now contains strangers. Some are younger, some are older, some are at different distances. The pattern becomes messy, and the conclusions become less reliable. Carefully identifying cluster members allows astronomers to do something powerful. They can study many stars whose history is partly shared. That turns star clusters into tools for understanding much more than clusters themselves. They help scientists test models of stellar evolution. They help measure distances. They reveal how stars of different masses change over time. They preserve information about the chemical conditions inside galaxies at different stages of galactic history. Ancient clusters can tell us about very early periods in the development of galaxies. Young clusters show us star formation, while the evidence is still relatively fresh. Disrupted clusters help reveal how galaxies rearrange their stellar populations. Even the Sun may once have belonged to a cluster. Our Sun formed around 4.6 billion years ago from material in a star-forming environment, and like many stars, it was probably not born completely alone. Its original stellar siblings have long since dispersed through the Milky Way. Finding them now would be extraordinarily difficult. After billions of years orbiting the galactic center, stars become mixed. Gravitational encounters alter their trajectories. The Milky Way does not carefully keep related stars beside one another for sentimental reasons. Some researchers have looked for possible solar siblings by comparing stellar motion, ages, and chemical composition, but identifying a definite family after such a long separation is difficult. Still, the possibility offers a useful reminder. When we look at the stars scattered across the night sky, we are seeing the results of an enormous amount of stellar rearrangement. Some stars are still living close to the companions with which they formed. Some are beginning to drift away. Some have been separated for hundreds of millions of years. Some belong to dense systems that may remain recognizable long after the Sun itself has changed beyond its present form. The galaxy is full of stellar families at different stages of dispersal. This is why astronomers cannot classify star clusters by appearance alone. A dense ball of stars and a loose young grouping may have very different structures, histories, and futures, yet both can tell us something about how stars form collectively. The categories become useful once we ask specific questions. How many stars are present? How tightly are they packed? Are they gravitationally bound? How old are they? Where are they located within their galaxy? Are they still surrounded by the material from which they formed? How long are they likely to survive? Those questions begin separating the crowded universe into recognizable kinds of stellar systems, and one of the most useful details is whether the stars have managed to leave their birthplace behind. Older clusters are usually exposed to view. Their original gas has been cleared away, leaving the stars visible against space. The youngest groups are different. Some have formed so recently that they are still sitting inside the molecular clouds that produced them. Visible light can struggle to pass through the surrounding dust, which means an apparently dark region of a nebula may contain an active population of newborn stars hidden from ordinary sight. To understand star clusters from the beginning, then, we need to go into those clouds before the stars have had time to spread out, before winds and radiation have cleared the neighborhood, and before gravity has revealed which members are going to remain together. Inside those dense regions of gas and dust, the first stellar groups are already forming. At this stage, calling them star clusters can almost feel premature. Many of the stars are difficult to see. Some have only recently begun shining. Others are still protostars, continuing to gather material from their surroundings. Disks of gas and dust remain around many of them, and the larger molecular cloud may still dominate everything we can see from the outside. These very young groups are known as embedded clusters. The word embedded is quite literal. The stars are embedded inside the material from which they formed. Instead of sitting against a clear background of space, they remain wrapped in a combination of molecular gas and tiny grains of dust that can block visible light surprisingly well. That makes an embedded cluster rather different from the familiar image of a star cluster as a clean collection of bright points. If you could approach one with ordinary human eyesight, assuming for a moment that approaching an active star-forming region were a sensible holiday plan, you might not see hundreds of newborn stars arranged neatly in front of you. You might see glowing gas, dark patches of dust, bright knots, and a few stars that have managed to become visible through gaps in the cloud. Many of the others would be hidden. This is one reason astronomers didn't always have a complete picture of how common clustered star formation is. Visible light observations show what the dust allows us to see. Infrared observations can reveal much more. Dust that blocks visible wavelengths is often more transparent to infrared radiation. Observing a molecular cloud in the infrared can therefore expose stars that seem to appear from nowhere when compared with an ordinary optical image. Nothing has actually appeared, of course. The stars were there all along. We have simply changed the kind of a light we use to look at them. It is a useful reminder that the universe we see with our eyes is only one version of the universe available to us. A dark cloud in visible light can contain dozens or hundreds of stars. A region that seems nearly empty may become crowded when viewed in the infrared. X-ray observations can reveal young stars in another way, because young stellar objects are often strong sources of X-rays due to intense magnetic activity. Astronomers can combine observations at several wavelengths and begin sorting out a scene that would otherwise be hidden behind dust. The process that created that scene began before any stars existed. A molecular cloud can contain enormous quantities of cold material spread across many light years. It is mostly hydrogen, along with helium, traces of heavier elements, and solid dust grains. The cloud is not equally dense everywhere. Some parts contain more matter than others. Gravity works on those denser regions. If a region becomes sufficiently dense and can no longer resist its own gravity, it begins to collapse. The collapse may divide the cloud into smaller structures, each of which can collapse further. Instead of the entire cloud falling directly into one enormous object, fragmentation allows many stars to begin forming within the same larger environment. The result is rarely orderly. Young stars may be scattered through filaments of dense material. Some form in compact groups, others appear along ridges where gas has accumulated. Several generations of star formation may overlap. Newly formed massive stars can affect nearby gas while other protostars are still assembling. The neat diagrams we use to explain star formation usually show one cloud becoming one protostar, then a star surrounded by a disk, and eventually a mature stellar system. That description is useful when focusing on one star. Zoom out, and the nursery is much busier. Stars are forming beside other stars that are also forming beside still more stars. All while gas moves through the region, radiation heats parts of the cloud, magnetic fields influence the material, and gravity tries to collect whatever it can. An embedded cluster is therefore not simply a finished cluster covered with dust. It is a cluster during construction. Some of its future members may not have finished forming. Some may continue gaining mass. Others may already be producing powerful radiation and winds. The amount of gas can still be substantial enough to influence the gravitational behavior of the entire system. That last point becomes important later. When we imagine a cluster, it is easy to think only about the gravitational pull of the stars, but during the embedded stage, gas contributes mass too. A young group may be sitting inside a much larger reservoir of material, and that material helps shape the gravitational environment in which the stars move. Then the stars begin removing it. Low-mass young stars can produce outflows. Massive stars are much more disruptive. They emit intense ultraviolet radiation, heating and ionizing nearby gas. Their stellar winds push against the surrounding material. Eventually, the most massive stars can end their lives as supernovae. All of these effects can clear gas away. From the point of view of someone who prefers tidy rooms, this sounds helpful. From the point of view of the cluster's gravity, it can be a serious change in circumstances. If enough gas is removed rapidly, the total gravitational pull holding the young system together decreases. Stars that have been moving inside the combined gravitational influence of stars and gas may suddenly find themselves in a system that cannot hold all of them. Some remain together, some drift away. This is one reason the embedded stage is important when trying to understand where later star clusters come from. We are seeing stellar groups before it is always clear what they will become. A few may emerge as recognizable bound clusters. Others will expand and dissolve into stellar associations or the general population of the galaxy. The newborn group does not arrive with a label attached. One of the best-known places to see this early stage is the Orion Nebula cluster, usually shortened to ONC, inside the Orion Nebula, M42, also catalogued as NGC 1976. Orion is useful because by galactic standards it is nearby. The Orion Nebula lies roughly 1,300 light-years from Earth, which makes it one of the closest major star-forming regions to us. The bright nebula itself is visible to the unaided eye under reasonably dark skies as part of Orion's sword. Through a telescope, it becomes much more obvious that something substantial is happening there. The Orion Nebula cluster contains thousands of young stars. Near its centre is the famous trapezium, a compact grouping dominated by 4 bright, massive young stars whose arrangement gives the group its name. These stars are not quietly waiting for everyone else to finish forming. Their ultraviolet radiation is changing the surrounding nebula. Gas is ionized and illuminated. Cavities are carved into the cloud. Radiation reaches the disks around nearby young stars and can strip material from them. Some of those externally illuminated disks have been observed directly. They're often called proplyds, short for protoplanetary disks. This means that in the Orion Nebula cluster we can examine stars that are young enough to retain the raw material from which planetary systems may develop, while nearby massive stars are already altering that material. It is a very different environment from the one around the Sun today. Our solar neighbourhood is comparatively quiet. The nearest stars are separated from us by several light years. There is no massive O-type star sitting nearby and bathing the solar system in powerful ultraviolet radiation. In a dense young cluster, neighbouring stars can be much closer, and the presence of a few very massive members can change conditions for everyone else. A small red star forming near a massive star does not get to ignore its neighbour. The radiation is there whether it approves or not. The Orion Nebula cluster has also challenged simple ideas about how clusters assemble. Studies comparing stellar ages across the ONC and another young cluster have suggested that stars near the outer parts can be older, on average, than stars nearer the centre. At first, that may sound backward. A very simple model might imagine a molecular cloud collapsing toward the middle, reaching the necessary density there first, producing the oldest stars at the centre, and then forming younger stars farther out. Real star-forming regions do not necessarily behave that neatly. Star formation can proceed through complex structures. Gas can flow. Smaller groups may merge. Dense central regions may continue forming stars after more dispersed populations have already appeared elsewhere. Embedded clusters preserve these details because we are seeing them before millions or billions of years of stellar motion have erased much of the evidence. Another excellent example lies in the same general part of the sky. NGC 2024 is the young cluster associated with the Flame Nebula. The Flame Nebula is located near Alnitak, the easternmost star in Orion's belt from our perspective, and lies about 1,400 light-years from Earth. In visible images, dark lanes of dust cross the bright nebula and give it the appearance that inspired its popular name. Behind and within that dust is a young cluster. NGC 2024 is one of those objects that makes the usefulness of infrared and X-ray astronomy immediately obvious. In visible light, the material in front of the cluster obscures much of what is happening. At longer wavelengths, the hidden stellar population becomes easier to examine. NASA's Chandra X-ray Observatory and infrared telescopes have been used to estimate the ages and masses of young stars in NGC 2024. Those observations produced an interesting result. As in the Orion Nebula cluster, researchers found evidence that stars toward the outer parts of NGC 2024 were generally older than stars closer to its central region. The age differences are measured in millions of years or less, not enormous fractions of cosmic history. That is exactly the scale that matters when dealing with newborn stars. For comparison, the The Sun is about 4.6 billion years old. A star that is 1 million years old has lived for roughly 2/10,000ths of the Sun's current age. At that point, calling a star young is not an attempt to make it feel better about itself. It really is young. Many stars in embedded clusters are still pre-main sequence stars. That means they have not yet settled into the long stable period of hydrogen fusion that defines most of a star's lifetime. A protostar forms as collapsing material becomes concentrated and heats up. As the object evolves, it continues contracting and may continue gathering mass through a surrounding disk and envelope. Eventually, when conditions in the core allow sustained hydrogen fusion, the star reaches the main sequence. The exact timescale depends strongly on mass. Massive stars evolve through their formation stages relatively quickly. Low-mass stars take longer to settle. This means an embedded cluster can contain objects at several closely related but distinct stages of youth. Some may be deeply buried protostars. Some may be young stars with thick disks. Others may have already cleared much of the material immediately around them. A cluster only a few million years old can therefore provide a surprisingly complicated population. Move much farther from Orion, in the direction of the southern constellation Vela, and we encounter another well-known embedded cluster, RCW-38. RCW-38 lies about 5,500 light-years away. Unlike the relatively nearby Orion regions, RCW-38 is distant enough that observing its individual low-mass members is more difficult. Even so, infrared telescopes have revealed a dense active stellar nursery, containing roughly 2,000 stars, including hundreds of young, hot stars and objects that are still forming. The designation CW comes from a catalogue of emission regions compiled by astronomers Rogers, Campbell and White Oak. Catalogue names are not always designed for charm. Astronomy contains objects with names such as the Flame Nebula and the Eagle Nebula, and then, sitting beside them in the filing cabinet, something called RCW-38. The universe supplies the spectacle. Astronomers supply the paperwork. RCW-38 is especially useful because it represents a more intense environment than many smaller nearby star-forming regions. Massive young stars occupy its central area. Their radiation and winds interact with the surrounding gas and with material around younger, lower-mass objects. Observations in visible light hide large portions of the cluster because of dust. Infrared instruments can penetrate much of that obscuration and reveal the stars behind it. In 2026, ESO released new infrared views of RCW-38 from the Vista telescope, showing the mixture of stars, gas, dusty structures, young stellar objects, and brown dwarfs inside this active region. Brown dwarfs are particularly interesting members of these environments. They form in ways related to stars but never acquire enough mass to sustain ordinary hydrogen fusion in their cores. The usual boundary is around 75 to 80 times the mass of Jupiter, although the exact value depends on composition. Below that limit, an object can still glow from the heat of its formation and undergo some nuclear reactions involving deuterium if it is massive enough, but it does not become a normal hydrogen-burning star. Embedded clusters therefore reveal not only stars but part of the broader population produced during star formation. The same collapsing cloud can generate massive stars, sun-like stars, low-mass red dwarfs, brown dwarfs, binary systems, and objects surrounded by disks that may eventually produce planets. Another nearby example gives us a slightly different view. NGC1333 lies in the Perseus molecular cloud, approximately 960 light-years away. It contains several hundred young stars forming within an environment of gas and obscuring dust. Unlike the bright central glare of Orion's trapezium, NGC1333 is a useful place for studying a less massive but still active clustered nursery. Hubble observations show illuminated gas and thick dark regions, but much of the young population remains hidden at visible wavelengths. Infrared observations uncover many of these stars and protostars. The region also contains numerous stellar outflows. When a protostar gathers material through a disk, not everything falls onto the young star. Some material can be launched outward along the system's rotational axis in narrow jets. These jets can move at high speeds and collide with the surrounding molecular cloud. Where the outflow strikes gas, it can produce shock-heated structures known as Herbig-Haro objects. So a newborn stellar cluster is not a passive collection of small stars quietly switching on. It is full of motion. Material falls inward, jets travel outward, disks rotate, stars move through the cloud, radiation heats gas, winds push material away. Dense regions continue collapsing while nearby regions are being disrupted. All of this happens while gravity continues trying to determine whether the stellar group will remain a group at all. That uncertain future raises one of the most important questions about embedded clusters: how many survive? The answer depends partly on what we mean by survive. A stellar population can remain recognizable for some time while expanding, even if it is no longer gravitationally bound. A smaller central portion may stay together while outer members escape. Several smaller groups within a larger star-forming complex may combine. Trying to take every embedded cluster and place it on a simple path toward one later cluster type does not work very well. Earlier models sometimes encouraged the idea that most stars formed in compact clusters and that many of those clusters were quickly destroyed when gas was expelled. Modern observations show a wider range of structures. Star formation can be highly hierarchical. That means stars can form in small groups inside larger groups, along filaments, inside dense cores, and across extended complexes without every population beginning as a single, smooth, round cluster. Some young regions already have structures that are unlikely to settle into long-lived bound clusters. Others contain dense concentrations that may survive after the surrounding gas disappears. The transition is gradual rather than a single moment when an embedded cluster suddenly becomes an exposed cluster. Dust begins thinning in some directions. Gas is cleared from central regions. Bright young stars become visible. The surrounding cloud breaks apart. More members can be seen at optical wavelengths. At some point, astronomers stopped describing the system primarily as embedded because its original molecular material no longer hides most of its stars. By then, the cluster may have expanded considerably. The stars that remain gravitationally connected continue moving together. Those that are no longer bound begin joining the wider galaxy. There is something particularly useful about catching a stellar population before that separation happens. Once stars are scattered through the Milky Way, reconstructing their shared birthplace becomes difficult. Inside an embedded cluster, the evidence is still concentrated in one location. The gas is present. The younger stars are present. Protostars are present. Disks are present. The effects of massive stars can be measured while neighbouring planetary systems are still being assembled. Astronomers can study the initial distribution of stellar masses, how frequently binary and multiple systems form, how disks evolve, how close encounters influence young stars, and how quickly feedback removes the remaining cloud. This also gives us context for our own beginning. The Sun almost certainly passed through a young phase involving a disk and surrounding star-forming material. Meteorites preserve evidence from the earlier solar system, and researchers have long investigated whether the Sun formed in a clustered environment containing nearby massive stars. Exactly what that original environment looked like remains uncertain. The Sun's siblings are no longer gathered around us. Whatever cluster or association contained them was dispersed long ago, leaving no convenient photograph of the family nursery. Embedded clusters let us observe other stars during the stage our own system passed through billions of years ago. Orion shows us thousands of young stars under the influence of massive trapezium stars. NGC 2024 shows a cluster still strongly obscured inside the Flame Nebula. RCW 38 shows a dense and energetic nursery containing roughly 2,000 stars far deeper in the Milky Way. NG C1333 shows hundreds of young objects forming within the Perseus molecular cloud, along with the outflows and dusty structures that accompany early stellar development. None of them is an exact copy of the Sun's birthplace. Together they show how many different forms stellar birth can take. Once the surrounding gas and dust have been cleared away, the surviving stars become much easier to recognize as a group. The cloud that once hid them is no longer the main feature. What remains is a collection of stars with a common origin, similar age, related motion through the galaxy, and enough gravitational connection to remain together for at least part of their lives. These are open clusters. They are called open because their stars are spread relatively loosely across space, allowing individual members to be distinguished rather easily. This is very different from the dense appearance of globular clusters, where thousands of stars can crowd together toward a bright central region. An open cluster usually looks less organized. There may be a concentration near the middle, but the overall shape can be irregular, with stars scattered across a broad area rather than arranged into a compact sphere. That slightly untidy appearance is not a flaw. It tells us something about what the cluster is and what is happening to it. Most open clusters contain anywhere from a few dozen to a few thousand stars. They form together from the same molecular cloud or from closely connected parts of a larger star-forming complex, and they usually occupy the disk of their galaxy. In a spiral galaxy such as the Milky Way, many are found in or near the spiral arms, where cold gas and active star formation are concentrated. This means that open clusters are often young by astronomical standards. Young, of course, needs some explanation when discussing stars. A cluster that is 100 million years old has existed for far longer than our species, longer than the age of many mountain ranges, and long enough for continents to move considerable distances. Astronomers may still describe it as young because a star like the Sun can remain on the main sequence for around 10 billion years. The universe has a very relaxed definition of youth. Open clusters can also survive for hundreds of millions of years, and a smaller number persist for several billion years. Their survival depends on their mass, density, orbit through the galaxy, internal gravitational interactions, and encounters with structures around them. What they generally do not do is remain unchanged. The moment an open cluster emerges from its birth environment, it has already started a long process of losing members. Stars move through the system at different speeds. Close gravitational encounters alter their motions. The galaxy pulls on the cluster as a whole. Giant molecular clouds can pass nearby. Spiral structure can disturb its orbit. Stars near the outer edges can gradually escape. The cluster may begin with hundreds or thousands of related stars and eventually leave only a dispersed trail of former members moving through the galactic disk. We can see this process at several different stages by comparing real open clusters. One of the most famous is Messier 45, the Pleiades. You may know it as the Seven Sisters. Under a reasonably dark sky, the Pleiades can be seen without a telescope in the constellation Taurus. Most people immediately notice 6 bright stars, although the group has been associated with 7 prominent stars in many cultures for a very long time. Those few bright points are only the most obvious members. Messier 45 contains more than 1,000 known stars associated with the cluster. It lies about 445 light-years from Earth and formed roughly 100 million years ago. That makes the Pleiades much older than the stars in the Orion Nebula cluster, but still very young compared with the Sun. The difference is visible in the environment. In Orion, large amounts of star-forming gas remain nearby. Many stars are still associated with disks, protostars and dense cloud material. In the Pleiades, the original birth cloud has been dispersed. The stars are exposed and moving together through the Milky Way. Some images of the Pleiades show blue nebulosity around its brightest stars. For many years, it was tempting to assume that this dust must be material left over from the formation of the cluster. That is not the leading interpretation today. The Pleiades appear to be passing through an unrelated region of interstellar dust. The stars illuminate that dust, producing reflection nebulosity. but the material is not necessarily the remains of the cloud that created them. The cluster has had plenty of time to leave its original nursery behind. Its most noticeable stars are hot and blue, which makes sense for a young population. Massive blue stars consume their nuclear fuel far more rapidly than stars like the Sun. If the cluster were several billion years old, those particular stars would no longer be present on the main sequence. Their existence immediately provides information about the age of the population. This is where open clusters become extremely useful to astronomers. Because the stars formed at approximately the same time and from similar material, scientists can compare stars of different masses while keeping age and initial composition relatively constrained. Imagine trying to understand how people age by studying random individuals from an entire country without knowing when any of them were born. You might observe different heights, appearances, and health conditions, but separating the effects of age from all the other differences would be difficult. Now imagine studying a large group whose birth dates are all nearly the same. Suddenly, differences between them become much easier to interpret. A star cluster provides something similar. The massive stars evolve quickly. Lower mass stars evolve slowly. Plot their brightness against their colour or temperature, and the resulting colour magnitude diagram reveals a recognisable sequence. The point where stars begin leaving the main sequence is especially important. Astronomers call this the main sequence turn-off. Massive stars reach that point first. As a cluster grows older, progressively lower mass stars begin leaving the main sequence. By comparing the observed turn-off with models of stellar evolution, astronomers can estimate the cluster's age. Open clusters have therefore been used for generations as testing grounds for our understanding of stars. The Pleiades provides a relatively young example. Move your attention across Taurus, and another famous open cluster shows what several 100 million additional years can do. This is the Hyades, catalogued as Melot 25. It forms a broad, V-shaped arrangement that helps define the face of Taurus in the night sky. The bright orange star Aldebaran appears to be part of that V, but it is not actually a member of the Hyades. Aldebaran lies much closer to us. It simply happens to sit in front of the cluster from our perspective. Astronomy provides these accidental photobombings quite regularly. The Hyades is the nearest major open cluster to the solar system. Its central population is roughly 150 light-years away, making it considerably closer than the Pleiades. It is also older. Estimates of its age depend somewhat on the stellar models being used, but values around 600 to 800 million years are common. NASA material often gives an age of about 625 million years, while studies that account for factors such as stellar rotation have produced ages closer to 800 million years. The exact number is less important for our present purpose than the difference between the Hyades and the Pleiades. The Pleiades is around 100 million years old. The Hyades has been travelling through the Milky Way for several times longer. That extra time has changed it. Its most massive original stars are already gone from the main sequence. Some completed their lives long ago. Other members have evolved into red giants or white dwarfs. The cluster itself is also being pulled apart. Gaia observations have helped astronomers identify extended tidal structures associated with the Hyades. Stars related to the cluster stretch far beyond the compact region, traditionally recognised in sky maps. That immediately changes what we mean when we say where the Hyades is. The part visible as a familiar cluster is only the denser remnant. Former and escaping members extend through a much larger volume of space. A cluster can therefore have more than one boundary depending on what you are measuring. There is the obvious visual group. There is the gravitationally bound core. There are stars close to escaping. There are tidal tails containing stars that have already been stripped from the main system, but still preserve related motions through the galaxy. From a photograph alone, these populations can be difficult to separate from unrelated stars around them. Gaia changed that problem dramatically. By measuring precise positions, distances, and motions for huge numbers of stars, astronomers can search for groups not merely by where stars appear in the sky, but by how they move through three-dimensional space. Two stars can look close together while being unrelated. Two stars separated by a large distance can retain evidence that they once belonged to the same system. Motion becomes part of the family record. The Hyades is particularly useful because its proximity allows stellar motions to be measured in great detail. Its stars appear to move toward a common point on the sky because the cluster is travelling through space as a group. This effect helped make the Hyades historically important for determining stellar distances and calibrating methods used elsewhere in astronomy. Nearby open clusters became some of the first steps in what astronomers call the cosmic distance ladder. Once the distance to a cluster is known, the apparent brightness of its stars can be compared with their true luminosity. Similar kinds of stars in more distant systems can then help extend measurements outward. A modest group of stars in Taurus therefore contributed to the much larger problem of measuring the scale of the universe. Open clusters have a habit of being more useful than their relaxed appearance suggests. Another cluster illustrates the same process from a slightly different direction. Messier 44, also catalogued as NGC 2632, is better known as Precep, or the Beehive Cluster. It lies in the constellation Cancer, approximately 600 light-years away, and contains around 1,000 stars. Under dark skies, the Beehive can be visible to the unaided eye as a faint misty patch. Binoculars resolve that patch into individual stars. This transformation is partly why open clusters are such satisfying objects for casual observing. You do not always need a large telescope. A hazy area that appears unimpressive to the eye can turn into dozens of separate stars with modest magnification. Precep is several 100 million years old and is often estimated at around 600 to 700 million years, putting it in roughly the same broad age range as the Hyades. That similarity is interesting for more than classification. The two clusters also have similar chemical compositions and motions, and astronomers have investigated whether they could share aspects of a common origin or broader star-forming history. Even when two clusters remain separate objects, comparing them allows researchers to test how stars of similar ages evolve under different conditions. The Beehive has also become useful in exoplanet research. Planets have been discovered around stars in open clusters, including giant planets associated with members of Praesepe. This matters because a star cluster gives researchers an approximate age for the planetary system. For an isolated star, determining age can be difficult. For a planet orbiting a well-studied cluster member, we have additional context. We know the star formed with the cluster. We can estimate when that happened. We can compare planetary systems belonging to stars of similar age. This helps researchers study how planetary systems change over hundreds of millions of years. Do giant planets migrate? How quickly do planetary atmospheres evolve? How long does intense stellar activity persist? How do planets around young stars compare with planets around mature stars such as the Sun? Open clusters provide populations in which some of those questions can be addressed more cleanly. They also contain stars with different rotation rates. Young stars often rotate relatively quickly. Over time, magnetized stellar winds carry away angular momentum, and many stars gradually slow down. For certain types of stars, rotation can therefore provide another clue to age. This has led to methods sometimes grouped under the term gyrochronology, in which stellar rotation is used as an age indicator. Clusters are essential for calibrating such relationships because we need populations whose ages can be estimated independently. The Pleiades gives us stars around 100 million years old. Praesepe and the Hyades provide older populations. Still older open clusters extend the comparison further. By examining rotation in each population, astronomers can see how stars gradually lose angular momentum. It is similar to having photographs of the same process at several different times, except the photographs are made of entirely different stars that happen to be useful substitutes for one another. The method is not perfect. Rotation depends on stellar mass, magnetic behavior, previous evolution, and other factors. Stars do not all slow down according to one simple universal schedule. Nature rarely provides a calibration curve without adding footnotes. But open clusters give us one of the best ways to study the pattern. Their usefulness continues when we examine chemical evolution across the Milky Way. Open clusters can be found at different distances from the galactic centre. Because their ages and chemical compositions can be measured, they help astronomers investigate how the disk of the Milky Way changed over time. The galaxy has not always contained the same mixture of elements. The earliest generations of stars formed primarily from hydrogen, helium, and small amounts of lithium produced in the early universe. Stars then manufactured heavier elements. Massive stars produced elements through nuclear fusion and distributed material through winds and supernova explosions. Other stellar processes added additional elements over time. New generations of stars formed from gas enriched by earlier generations. Open clusters preserve samples of the chemical state of the Milky Way at different locations and times. A cluster that formed several billion years ago contains a record of the gas available when it formed. A cluster created recently records more recent conditions. By comparing clusters across the disk, researchers can study chemical gradients and the movement of stellar populations through the galaxy. The term open cluster therefore describes a relatively simple-looking object that participates in several much larger problems: star formation, stellar evolution, planet formation, galactic structure, chemical enrichment, dynamics, distance measurement. It is difficult for several hundred stars to mind their own business. There is also an important reason we tend to associate open clusters with spiral arms. Spiral arms contain concentrations of gas, including molecular clouds where new stars form. The brightest massive stars do not live very long, so young star clusters containing those stars remain relatively close to the regions where they were created. Seen in another spiral galaxy, bright young clusters can help trace the arms, but the connection is not permanent. An open cluster orbits the galactic centre. The spiral pattern and the stars in the disk do not necessarily move together in a simple locked arrangement. Over time, clusters can leave the specific spiral environment in which they formed. Older open clusters may be found between arms. Their positions today are not always the positions where they were born. The Milky Way itself complicates the view because we are observing the disk from inside it. Dust blocks our vision in many directions. Distant clusters become difficult to detect. Clusters on the far side of the galaxy may be hidden behind enormous quantities of interstellar material. This is one reason the number of known open clusters keeps changing as surveys improve. NASA describes the Milky Way as containing more than 1,000 known open clusters, while modern catalogues based on large surveys contain several thousand candidates and confirmed systems depending on the classification criteria being used. Gaia has been particularly effective at finding clusters that do not immediately stand out in images. A cluster does not have to look impressive to be physically real. If its stars occupy related positions in space, share similar motions, and follow a consistent age pattern, the group can emerge from the data even when our eyes would never have selected it. In some cases, modern surveys are also showing that familiar clusters are much larger in a dynamical sense than the traditional bright central grouping suggested. The Pleiades provides a particularly interesting recent example. For generations, M45 was treated as the recognizable group centered on the famous bright stars in Taurus. In 2025, researchers combining data from NASA's TESS mission and ESA's Gaia mission reported evidence for what they called the Greater Pleiades Complex. Instead of only examining stars currently concentrated around M45, the researchers searched for stars sharing related patterns of rotation and motion. They identified thousands of possible stellar relatives extending far beyond the traditional boundaries of the cluster. The interpretation does not mean that all of those stars are still members of one compact gravitationally bound object. It means the history of the Pleiades may be written across a much larger population than the familiar patch of sky we call M45. This is exactly the kind of thing we should expect from open clusters. Their present appearance is temporary. The group we see is one moment in a process that began inside a molecular cloud and may end with its stars scattered across thousands of light years. The destruction is not usually dramatic. There is no moment when the cluster explodes and everyone leaves. Instead, the system gradually becomes less able to keep its stars together. Imagine a cluster containing 1,000 stars. They all contribute to the cluster's gravitational field, but they also continually interact. A passing star pulls slightly on another. That star changes speed. Over many encounters, energy is redistributed throughout the system. Some stars lose orbital energy and move toward the center. Others gain energy and move outward. Low-mass stars can be particularly vulnerable to being pushed toward the outskirts and eventually escaping. This slow loss is often described as evaporation. The name suggests that the cluster somehow becomes warm enough for stars to boil away. Fortunately, no boiling is required. It is a statistical gravitational process. Given enough encounters, some stars acquire velocities that allow them to leave. The galaxy assists. The Milky Way's gravitational field produces tidal forces across the cluster. The side closer to the galactic center experiences a slightly different pull from the side farther away. The effect can stretch the system. Passing molecular clouds can provide stronger disturbances. A close encounter with a massive cloud may alter the velocities of many cluster stars and accelerate the disruption process. Crossing different parts of the galactic disk can also disturb the cluster. Each event may remove only part of the population, but open clusters can orbit the Milky Way many times during their lives. Eventually, the losses add up. The surviving cluster becomes smaller, its tidal tails become larger. At some point, identifying the original system becomes difficult. The Sun may represent the end result of precisely this process. It likely formed in a group containing other stars about 4.6 billion years ago. We do not see a 4.5 billion-year-old cluster surrounding the Sun today. Its original siblings have been dispersed. They continue orbiting the Milky Way, but the galaxy has had billions of years to rearrange their positions. Some may be relatively close in galactic terms. Others may have migrated substantial distances. Trying to identify one now requires comparing age, motion, and detailed chemical composition, while accounting for the gravitational evolution of the galactic disk over immense periods. The family gathering has become inconveniently large. Not every open cluster disappears quickly, however. Some survive for several billion years. One famous example is NGC 6791, an unusually old and massive open cluster that is around 8 billion years old. Objects like NGC 6791 are valuable precisely because they are unusual. An open cluster surviving that long has endured a great deal of gravitational disruption. Its old stellar population allows astronomers to examine late stages of stellar evolution, while knowing that the stars share a related history. White dwarfs become especially useful in older clusters. A white dwarf is the dense remnant left after a low or intermediate mass star reaches the end of its normal fusion life, expands through giant phases, and loses its outer layers. Because white dwarfs cool with time, populations of them can provide another method for estimating cluster ages. The oldest open clusters therefore allow different clocks to be compared. Main sequence turn-off ages, white dwarf cooling ages, stellar rotation where applicable, chemical information, binary evolution. A cluster that looks like a loose gathering through a telescope can become a test involving several branches of astrophysics at once. Binary stars are another part of the picture. Many stars form in pairs or larger multiple systems. Inside a cluster, binaries interact with the surrounding stellar population. A sufficiently close pair can behave gravitationally like a compact energy source during encounters. Passing stars can alter binary orbits, while binaries can transfer energy to other stars. In dense portions of a cluster, these interactions contribute to the cluster's long-term evolution. Occasionally, stellar encounters can produce objects that appear oddly young. One important example is a blue straggler. In a color magnitude diagram of an old cluster, most massive blue stars should already have evolved away from the main sequence. Yet sometimes a star appears bluer and brighter than the expected turn-off, as though it somehow failed to receive the cluster's schedule. Blue stragglers are thought to form through processes such as stellar mergers or mass transfer within binary systems. They are reminders that stars inside clusters do not evolve entirely independently. Neighbours matter. Binary companions matter. The local gravitational environment matters. The cluster is not simply a box containing stars of one age. It is a dynamic environment whose members influence one another. That environment changes as the system disperses. In a young open cluster, the density may still be high enough for relatively frequent interactions. Later, as the stars spread out, encounters become rarer. Eventually, former members become ordinary field stars in the galactic disk. A star passing through our neighbourhood today may once have belonged to a recognisable open cluster, whose name has been lost because the cluster itself no longer exists. This makes open clusters temporary structures, but extremely useful ones. They catch stars during a period when their shared origin is still visible. The Pleiades, M45, shows a young exposed population roughly 100 million years after formation. The Hyades Melotte 25 shows a more mature group, whose stars and tidal structures are already spread across a large region. Precep, M44 or NGC 2632, gives us another several 100 million-year-old population, and a place to study stars and planets with a shared age. Older systems such as NGC 6791 show that a few open clusters can remain recognisable for billions of years. Placed beside embedded clusters, they also give us a sequence. Stars form within molecular clouds. Young groups emerge from their gas and dust. Some remain sufficiently concentrated to become exposed open clusters. The clusters orbit through the galactic disk. Their stars evolve. The galaxy pulls at them. Members escape. Their recognisable boundaries become less distinct. Eventually, much of the original population joins the wider galaxy. This sounds like a long time because, from our perspective, it is. For the Milky Way, it is routine. Open clusters are continuously forming and continuously dissolving. While one cluster is disappearing into the disk, another is emerging from a molecular cloud elsewhere. There is no need for the galaxy to preserve individual clusters forever. Their stars remain. The material continues circulating, new molecular clouds form. Later generations appear. The cluster is one stage in the organisation of stellar populations. Open clusters show what happens when a stellar family remains loose enough for the galaxy to gradually pull it apart. The next kind shows what happens when gravity has had billions of years to hold a much denser one together. Globular clusters are among the most crowded stellar systems we can observe without moving into the central regions of galaxies themselves. Instead of a few hundred or a few thousand stars spread loosely across space, a globular cluster can contain hundreds of thousands of stars packed into a roughly spherical structure, and the largest examples contain millions. They also tend to be old, very old. Many formed during the early history of their galaxies, when the Milky Way was still assembling, and the Sun would not appear for billions of years. The stars we see inside them today are therefore survivors from an earlier period of cosmic history. This is immediately different from most open clusters. Open clusters are strongly associated with the galactic disk, where molecular clouds continue producing new stars. Globular clusters are commonly found in the halo and bulge, distributed above and below the thin disk and orbiting the centre of the galaxy, along paths that can carry them far from the regions where most current star formation takes place. The Milky Way has about 150 known globular clusters. That may sound like a small number compared with the enormous population of stars in our galaxy, but each cluster can contain enough stars to make an entire open cluster look rather underprepared. Their structure also gives them a very different appearance. An open cluster such as the Pleiades has enough space between its bright members that you can easily recognise individual stars. A globular cluster becomes progressively denser toward its centre. Through a small telescope, the outer stars may resolve into separate points while the central region remains a concentrated glow. With larger telescopes, more stars appear. With the Hubble Space Telescope, the core can become an extraordinary field of individual stars packed so closely together that almost every part of the image contains another point of light. The reason for the approximately spherical shape is gravity. A globular cluster has enough mass concentrated into a relatively compact region that the stars remain strongly bound as a system. Instead of gradually dispersing over a few 100 million years in the way many open clusters do, globular clusters can survive for most of the age of the universe. That does not make them permanent. Stars still escape. The galaxy still pulls on them. Their interiors still evolve. But the process is usually much slower because there is simply much more gravity keeping the system together. One famous example makes the difference easy to appreciate. Messier 13, also catalogued as NG C6205 and commonly called the Great Hercules Cluster, lies about 25,000 light-years from Earth in the constellation Hercules. It contains more than 100,000 stars. Through binoculars, M13 looks like a fuzzy circular patch. A modest telescope begins resolving stars around its edges. Larger instruments reveal an increasingly dense population toward the centre. Charles Messier added the object to his catalogue in 1764, although Edmund Halley had recorded it decades earlier. Early observers could not easily tell what the hazy object actually contained because their telescopes lacked the resolving power needed to separate the stars. Today we know that the haze is not gas, it is starlight. Thousands upon thousands of stars overlap from our perspective until their combined light creates what looks like a continuous glow. If we could move much closer to M13, the cluster would stop looking like a compact patch and become a three-dimensional swarm. The stars are spread across a region many light-years wide. They orbit within the gravitational field produced by the cluster as a whole, passing through the central region and moving back outward again on complicated paths. The word crowded needs some context here. Even in a globular cluster, stars are not usually close enough to collide constantly. Space remains extremely large compared with the physical size of a star. But compared with our neighbourhood around the Sun, the central regions of a globular cluster can be remarkably dense. The nearest star system to our own is more than 4 light-years away. Place the Sun inside the dense centre of a globular cluster, and several stars could be considerably closer than that. The night sky from a hypothetical planet there would therefore be very different. Many nearby stars could appear much brighter than the stars we see from Earth. Some might be bright enough to remain visible even during the planet's daytime, depending on the exact environment. It sounds attractive until you remember that dense stellar environments come with complications. Close gravitational encounters are more common. Binary systems can be disturbed. Stars can exchange energy. Planetary systems may be altered by passing stars, especially if planets orbit far from their host. The same density that makes a globular cluster visually impressive also turns it into a very active gravitational environment. And over billions of years, small interactions become important. Suppose 2 stars pass near each other. They do not need to collide. Their gravity changes both trajectories. One may gain a small amount of kinetic energy, the other loses some. Now repeat this process with hundreds of thousands of stars over billions of years. The cluster gradually redistributes energy among its members. Astronomers describe an important part of this process using the idea of dynamical relaxation. A globular cluster begins with stars of different masses moving through the system. Through repeated gravitational encounters, the distribution of energy changes. More massive stars tend to lose kinetic energy and move toward the centre, while lower mass stars are more easily pushed toward the outer regions. This produces mass segregation. We encountered the same idea in younger clusters, but globular clusters have had far more time for the process to operate. A good example is 47 Tucanae, also catalogued as NGC 104, located about 16,700 light-years away in the southern constellation Tucana. 47 Tucanae is one of the brightest globular clusters visible from Earth. It spans roughly 120 light-years, and contains an enormous stellar population, with estimates reaching close to 1 million stars. Hubble observations of 47 Tucanae have allowed astronomers to measure the motions of tens of thousands of individual stars. Those measurements give us something much better than a still image. They allow researchers to watch the internal organization of the cluster change over time. Heavier stars tend to become concentrated toward the center. Lower mass stars are more widely distributed. White dwarfs provide a particularly interesting case. A star like the Sun eventually becomes a white dwarf after passing through the red giant phase and losing its outer layers. When that happens, the remaining stellar core has much less mass than the original star. The object has effectively changed its place in the cluster's mass hierarchy. Observations of 47 Tucanae have shown white dwarfs moving outward from the crowded central region as the cluster gradually sorts its stellar population by mass. Nobody needs to direct traffic. Gravity does the sorting. The process takes a very long time, which is fortunate because a million-star traffic system would otherwise require an alarming amount of paperwork. The dense environment also creates objects that look as though they should not belong in such an old population. Blue stragglers are one of the best examples. A globular cluster may be more than 10 billion years old. Its original massive blue stars should have exhausted their fuel long ago. Massive stars live fast. They consume hydrogen rapidly, evolve away from the main sequence and eventually become stellar remnants. Yet when astronomers examine old clusters, they sometimes find blue, relatively luminous stars sitting in regions of a color magnitude diagram, where ordinary stars of the cluster's age should no longer exist. They appear younger than their neighbours. They have not actually been quietly ignoring stellar aging for 10 billion years. Instead, blue stragglers are thought to gain mass later in their lives. One route involves binary systems. If two stars orbit each other closely, material can move from one star to the other as their evolution changes. The receiving star gains mass and can become hotter and brighter, making it appear younger than the surrounding population. Another route involves stellar mergers or close encounters. Two stars can combine, producing a more massive star with properties unlike those expected from an ordinary member of the cluster. 47 Tucanae contains a substantial population of blue stragglers, particularly in its crowded central regions. This is important because globular clusters were once described rather simply as populations in which all stars formed at the same time and then evolved independently. That picture is useful as a first approximation. The real clusters are more complicated. Their stars interact. Binary systems evolve. Some stars merge. Compact remnants move through the population. Several globular clusters also contain evidence for more than one stellar population. The stars may share a broadly ancient history, while showing differences in chemical composition that indicate the cluster's early evolution was not one single, instantaneous burst of star formation. 47 Tucanae has provided evidence for distinct stellar populations whose ages differ by less than about 100 million years. Compared with a cluster that is billions of years old, 100 million years is not much. But it is enough to show that the formation of some globular clusters was more complicated than creating all their stars at once, and then closing the doors. That problem becomes much more obvious when we look at Omega Centauri. Omega Centauri, NG C5139, is the largest and brightest known globular cluster associated with the Milky Way. It lies roughly 17,000 light-years away in the constellation Centaurus and contains around 10 million stars. Its diameter is about 450 light-years. That is enormous for a globular cluster. For comparison, 47 Tucanae spans roughly 120 light-years. Omega Centauri is not just a slightly larger version. It is unusually massive, unusually complex, and has been causing astronomers classification difficulties for quite some time. Its stars do not all have the same chemical composition. Different populations show different abundances of heavier elements, suggesting that star formation continued through multiple episodes, or that the system retained material enriched by earlier generations. That is difficult for an ordinary globular cluster. Supernova explosions and stellar winds can eject gas at high speeds. A cluster needs substantial gravity if it is going to retain enough material to produce later populations. Omega Centauri apparently had access to a deeper gravitational potential than we would expect from a simple cluster. One explanation is that it may not have started life as an ordinary globular cluster at all. It may be the remaining nuclear region of a dwarf galaxy that was absorbed by the Milky Way. Imagine a small galaxy orbiting our own. Over time, the Milky Way's gravity strips away its outer stars. The dwarf galaxy becomes smaller with each encounter. Eventually, most of the original system disappears into the Milky Way's halo, leaving behind only its dense central region. That remnant could resemble an unusually massive globular cluster. Omega Centauri has several properties that make such an origin plausible, although the details of its history are still being investigated. This immediately tells us something important about the category itself. Globular cluster describes what an object is like now. It does not guarantee that every globular cluster formed through exactly the same process. Some may have developed as extremely massive star clusters. Others may have arrived through mergers with smaller galaxies. The Milky Way has grown partly by absorbing other systems, and globular clusters can preserve evidence of that history. Their orbits provide clues. Some globular clusters move around the Milky Way in directions or along trajectories suggesting that they may have been brought in by galaxies that merged with ours. This makes the halo a kind of archaeological record. The stars and clusters moving through it do not all have to share one birthplace. Some formed in the early Milky Way. Others may have formed inside smaller galaxies that no longer exist as independent systems. The clusters survived while their original galaxies did not. Their chemistry helps researchers separate those histories. Globular clusters are generally poor in elements heavier than hydrogen and helium compared with younger populations such as the Sun. Astronomers call this low metallicity. Remember that in astronomy, a metal is essentially anything heavier than helium, a definition that continues to make chemists slightly uneasy. A metal-poor star contains a smaller proportion of those heavier elements. That usually indicates that the star formed early in cosmic history, before repeated generations of stars had enriched interstellar gas with elements produced through stellar fusion and explosions. The first stars formed from material dominated by hydrogen and helium. Those stars created heavier elements. When some of them died, they released that material into space. Later stars formed from increasingly enriched gas. Globular clusters therefore give astronomers access to populations formed when galaxies were chemically younger. That does not mean every globular cluster has identical metallicity. Far from it. Different clusters show different chemical compositions, and those differences can help reveal where and when they formed. A metal-poor cluster moving through the outer halo may have a different history from a somewhat more metal-rich cluster associated with the galactic bulge. Omega Centauri takes the situation further by containing multiple populations with a range of chemical properties inside the same system. There is another reason old clusters are especially useful. Their stars have had enough time for many stages of stellar evolution to occur. The massive stars disappeared billions of years ago. Stars with lower masses have gradually evolved into red giants, horizontal branch stars, white dwarfs, and other late-stage objects. Neutron stars can remain after the supernova explosions of massive stars. Some of those neutron stars become pulsars. A pulsar is a rapidly rotating neutron star whose magnetic field directs beams of radiation through space. If those beams sweep across Earth, we detect regular pulses. Globular clusters contain far more millisecond pulses than we might expect from simply taking an ordinary region of the galaxy with the same number of stars. A millisecond pulsar can rotate hundreds of times per second. That is an extraordinary speed for an object containing more mass than the Sun compressed into something roughly the size of a city. Many millisecond pulsars are thought to have been spun up through interactions with binary companions. Matter flows from the companion onto the neutron star. That transfer adds angular momentum and increases the neutron star's rotation rate. Dense globular clusters are good places for producing unusual binary arrangements because stars encounter one another more frequently. A neutron star that might remain isolated in the galactic field can exchange companions through gravitational encounters inside a cluster. Binary systems can be broken apart, new ones can form. A passing compact object can replace one member of an existing binary. A cluster core therefore becomes a place where stellar evolution and gravitational dynamics repeatedly interfere with one another. Globular clusters can also contain X-ray binaries in which a neutron star or black hole accretes material from a companion. The infalling material heats up and emits X-rays. Finding such systems helps astronomers study compact objects under conditions that are difficult to reproduce elsewhere. Black holes are particularly interesting. For a long time, astronomers debated how many stellar mass black holes could remain inside old globular clusters. The massive stars that created them died early. After formation, gravitational interactions could eject black holes from the cluster, especially because the more massive objects tend to sink toward the center, where they encounter one another. Modern observations and simulations suggest that at least some clusters can retain black hole populations for long periods. There is also an ongoing search for intermediate mass black holes. These hypothetical objects would sit between stellar mass black holes, typically a few to tens of solar masses, and the supermassive black holes containing millions or billions of solar masses found in galactic centers. A dense globular cluster seems like a reasonable place to look. Perhaps repeated stellar collisions or black hole mergers could gradually build a larger object. Claims for intermediate mass black holes in particular clusters have been debated because the motions of stars in a dense core can be interpreted in more than one way. A concentration of unseen stellar remnants can sometimes imitate the gravitational effect of a single larger black hole. Omega Centauri has been one of the important targets in this discussion. The possibility is fascinating, but globular clusters have taught astronomers to be careful about assuming that every invisible mass in a crowded center must be one object. Sometimes the answer may be many dark objects rather than one very large one. The cluster itself also changes structurally over time. As mass segregation continues, heavier objects move inward. The core can become denser. Under certain conditions, a cluster can enter a phase called core collapse, in which the central region contracts and the stellar density increases substantially. At first, this can sound backward. You might expect a gravitational system to settle into a stable arrangement after billions of years. Instead, gravitational systems have some peculiar thermodynamic behavior. As stars in the core interact and transfer energy outward, the core can lose energy and contract. Contraction makes the inner stars move faster. That can drive further energy transfer. The process can continue until binaries and other interactions provide enough energy to slow or reverse the contraction. Binary systems act rather like energy reservoirs. A close binary can interact with passing stars and become more tightly bound. The passing star carries away some energy, heating the surrounding cluster dynamically. This can support the core against further collapse. None of this is visible as rapid movement to a human observer. A globular cluster looks practically unchanged over a lifetime. Its dynamics become obvious only when we combine long observations, precise measurements, simulations, and the willingness to consider a timescale on which 1 million years counts as a small interval. The galaxy is also working on the cluster from the outside. Globular clusters orbit the Milky Way and experience its tidal field. As a cluster moves through regions of stronger gravitational influence, especially when passing closer to the galactic center or through the disk, stars can be stripped away. Those stars may form tidal tails and stellar streams along the cluster's orbit, so even a globular cluster can dissolve. It is simply much better at postponing the process. Some clusters we see today may be only remnants of systems that once contained many more stars. Others may eventually be destroyed entirely, adding their populations to the halo and bulge. That means the approximately 150 globular clusters currently associated with the Milky Way are survivors. There may once have been more. Some were disrupted. Some may have merged into the central regions of the galaxy. Some contributed stars to the halo. The clusters still present today are the ones whose masses, structures and orbits allowed them to persist for billions of years. That survival is what makes them such useful records of galactic history. Messier 13 shows a classic dense globular cluster containing more than 100,000 ancient stars about 25,000 light-years away. 47 Tucanae NGC 104 contains up to around 1 million stars and allows us to observe stellar sorting, blue stragglers, white dwarfs, compact objects and distinct populations within one gravitationally bound system. Omega Centauri NGC 5139 pushes the category towards something far more complicated, with around 10 million stars, multiple stellar populations, and evidence suggesting that its past may involve something larger than an ordinary cluster. Look at those 3 objects alone, and the label globular cluster begins to cover quite a range. They're all dense, they're all old, they're gravitationally bound, they all orbit the Milky Way. Beyond those broad similarities, their histories can be remarkably different. This is why globular clusters matter for more than simply understanding how tightly stars can gather. Their oldest members provide estimates related to the age of the Milky Way. Their chemical compositions reveal the conditions from which early stars formed. Their motions preserve evidence of ancient mergers. Their white dwarfs provide clocks. Their binary stars show what happens when stellar systems spend billions of years in crowded environments. Their pulsars allow extraordinarily precise measurements of dense stellar systems. Their tidal tails reveal the gravitational field of the galaxy around them. Even their gradual destruction tells us how the Milky Way has changed. For something that looks through binoculars like a fuzzy dot, that is quite a workload. And there is one more contrast worth keeping in mind. A globular cluster survives because its stars remain strongly connected by gravity. A typical open cluster is less tightly bound and gradually loses its members. But there are also stellar families that begin together without ever becoming a compact, long-lived cluster at all. A stellar association can be difficult to recognize in an ordinary photograph. Its members may be spread across tens or even hundreds of light years. There may be no obvious center, no compact core, and no clean boundary that tells you where the group ends. Some members can sit far apart on the sky, mixed with unrelated foreground and background stars. What connects them is their history. The stars formed in the same broad, star-forming environment are usually similar in age, and move through the galaxy in related ways. Unlike the stars in a strongly bound cluster, however, the association as a whole does not have enough gravitational binding to keep all of its members together indefinitely. They are already dispersing. This does not necessarily mean something catastrophic happened. For a long time, astronomers often pictured associations as the remains of compact clusters that expanded after young stars expelled the gas surrounding them. Remove enough gas quickly, reduce the gravitational mass holding everything together, and the stars spread outward. That certainly can happen. Modern observations, especially those from ESA's Gaia mission, have shown that the full story is more complicated. Many young associations contain several subgroups, filaments, clumps, age differences, and different patterns of motion. Some may never have existed as one compact cluster at all. Instead, stars can form across a large, structured molecular cloud in several related groups, and begin dispersing from an already extended arrangement. The idea of a stellar family still works. The family may simply have lived in several houses from the beginning. The concept of stellar associations became important in the 20th century through the work of Armenian astrophysicist Victor Ambatsumian. In 1947, he argued that certain loose groups of very young stars were physically related despite appearing too spread out to remain gravitationally bound for long periods. That last detail was crucial. If a group is unbound and still recognizable, it cannot be extremely old. Given enough time, its stars would have moved apart and blended into the general stellar population of the galaxy, so the existence of stellar associations provided strong evidence that star formation was not something that happened only in the distant past. New stars were still being created in the Milky Way. Today, associations are commonly identified using age, distance, velocity, chemical properties, stellar type, and precise measurements of motion. Historically, astronomers divided them into several broad categories, based on the kinds of stars and surrounding material that made the association noticeable. 3 of the best known are OB associations, T associations, and R associations. The boundaries are not absolute. One star-forming complex can contain massive O stars, low-mass T Tauri stars, reflection nebulae, compact clusters, and expanding unbound populations at the same time. The labels are useful ways of describing what dominates the observed population, not 3 entirely separate manufacturing methods for stars. The easiest type to notice across large distances is usually the OB association. The letters O and B refer to stellar spectral classes. O-type stars are among the hottest, most massive, and most luminous normal stars. B-type stars are somewhat cooler and less massive, although calling a B star modest would be unfair when many are still several times the mass of the Sun, and thousands of times as luminous. These stars are bright, very bright. A single massive O-type star can emit more energy than tens of thousands of suns. Put several of them into one young stellar population, add dozens or hundreds of B stars, and the association can remain noticeable even from a considerable distance. That does not mean an OB association contains only O and B stars. This is an important point. Low-mass stars are much more common. For every spectacular massive member drawing attention to the region, there can be many fainter stars that form during the same star-forming episodes. The association receives its name from the stars that make it easiest to identify, not because the lower mass population forgot to attend. One of the most important examples is the Scorpius-Centaurus association, usually called SCO-CEN or SCO-OB2. It is the nearest major OB association to the solar system, spread across a large region in the direction of Scorpius, Lupus, Centaurus, and neighbouring southern constellations. SCO-CEN is traditionally divided into 3 main subgroups: Upper Scorpius, Upper Centaurus Lupus, and Lower Centaurus Crux. Their names make them sound like administrative districts created by astronomers who had run out of imagination, but the divisions correspond to real differences in the stellar populations. Upper Scorpius is younger. Modern estimates often place much of its population at around 10 million years old. Upper Centaurus Lupus and Lower Centaurus Crux are generally older, around 16 million years, although each subgroup contains internal age structure, and the exact numbers depend on the method being used. That spread in age immediately tells us that SCO-CEN was not produced in one perfectly synchronized event. Star formation occurred across a large region over millions of years. One part formed stars, another followed. Massive stars evolved quickly. Winds and radiation changed the gas. Some massive stars exploded. Other areas continued producing new stars while older populations were already expanding through space. The entire SCO-CEN complex now covers such a large area that the stars would not look like one obvious group if you simply stood outside and took a photograph. Their positions and motions reveal the connection. This is where Gaia has become extremely useful. By measuring stellar parallaxes, proper motions, and other properties with very high precision, astronomers can separate young populations from unrelated stars occupying the same part of the sky. The members of SCO-CEN do not all move in perfectly parallel lines. The region contains substructure. Different groups have their own motions, some are expanding, some overlap in position while remaining distinguishable in velocity. The old mental picture of one neat association expanding outward from a single point does not describe the observations particularly well. Instead, SCO-SEN appears to preserve the complicated structure of the star formation that created it. The massive stars are only part of that record. Researchers have identified large numbers of lower mass K and M-type members, along with brown dwarfs and stars still retaining circumstellar disks. In Upper Scorpius, some stars remain young enough to have disks containing gas and dust, even though the wider association has already expanded substantially. That allows astronomers to study planet formation in a population whose age is constrained by its membership. A 10-million-year-old star with a disk is very different from a 10-million-year-old star whose disk has already disappeared. Put hundreds of stars of roughly related age in the same association, and researchers can ask how disk survival depends on stellar mass, environment, multiplicity, and other factors. The massive members of an OB association also reshape the interstellar medium around them. An O star emits intense ultraviolet radiation capable of ionizing hydrogen over a large region. Its stellar wind pushes material outward. Several massive stars acting together can inflate large cavities in surrounding gas. Later, some explode as core collapse supernovae. Repeated winds and supernovae can help create enormous low-density bubbles surrounded by shells of compressed material. The Scorpius-Centaurus association has been studied in connection with the structure of the local interstellar environment around the Sun. Our solar system currently lies inside a region of unusually low-density hot gas commonly called the local bubble. Its detailed formation history is still studied, but multiple supernovae from nearby young stellar populations, including stars associated with SCO-SEN, are thought to have contributed to shaping the surrounding region. So an association does not need to remain gravitationally bound to have a major effect. Its stars may be drifting apart while collectively altering hundreds of light-years of galactic space. Another OB association is especially familiar because we have already visited parts of it without using the larger name. Orion OB1 is the extended young stellar population associated with the Orion star-forming complex. The Orion Nebula cluster belongs to the youngest part of this wider environment, but the association extends far beyond the bright nebula. Traditionally, Orion OB1 has been divided into 4 major subgroups known as OB1A, OB1B, OB1C, and OB1D. OB1A includes an older population northwest of Orion's belt. OB1b is associated with stars around the belt itself, including the region containing Alnitak, Alnilam, and Mintaka. OB1c is associated with stars around Orion's sword. OB1d includes the youngest population in and near the Orion Nebula and the trapezium. That classical picture is useful, but Gaia and large spectroscopic surveys have revealed a much more detailed structure. Instead of 4 simple populations, researchers find many smaller groups with distinct distances, ages, and velocities. Thousands of young stars in the direction of Orion can be separated into numerous related structures. This is one of the recurring lessons of modern star cluster research. When our measurements become more precise, nature usually becomes less tidy. Orion is not one cluster sitting inside one association produced during one event. It is an extended star-forming complex containing clouds, embedded groups, exposed clusters, massive stars, low-mass stars, expanding populations, and subgroups at different stages of development. Some stars remain near the gas from which they formed. Others have travelled farther away. Some populations are still compact. Others are clearly dispersing. The broad term Orion OB1 remains useful because the massive O and B type stars identify a major young stellar complex. But the detailed history requires far more than 4 labels. This also explains why associations can be difficult to classify by appearance. Take away the brightest stars and much of the group becomes visually ordinary. A low-mass star in an OB association does not carry a sign saying that it formed near an O star 10 million years ago. Astronomers look for youth indicators. One of them is lithium. Young low-mass stars contain lithium inherited from the material from which they formed. Over time, conditions inside the star can destroy lithium through nuclear reactions. The exact depletion rate depends on stellar mass and structure, but strong lithium absorption in the spectrum of an appropriate low-mass star can indicate that it is young. X-rays provide another clue. Young stars often have intense magnetic activity and can produce strong X-ray emission. Rotation can help as well. Many young stars rotate quickly before magnetic braking gradually slows them over longer periods. Then there are circumstellar disks. A disk is strong evidence that a star is in an early stage of development, although disks disappear on timescales much shorter than the lifetime of a low-mass star. These clues become particularly important when we move from OB associations to T associations. The T does not stand for temperature. It comes from T Tauri, the prototype of an entire class of young stars. T Tauri itself is located in the Taurus star-forming region and is actually a multiple stellar system. Its name became attached to low-mass pre-main sequence stars that have emerged enough to be observed as stars, but have not yet settled onto the main sequence in the way the Sun has. T Tauri stars can be variable. They may have disks. Some are actively accreting material. They can produce jets and outflows. They frequently show strong magnetic activity. Their spectra can contain emission lines associated with hot gas and accretion. A group containing many such stars can be described as a T association. Unlike an OB association, a T association does not need a large population of massive O and B stars to advertise its existence. The emphasis is on low-mass young stars. One of the classic examples is the Taurus Auriga association. Taurus Auriga lies roughly 140 parsecs, or about 450 light-years from the Sun, and is one of the nearest major regions of low-mass star formation. Its stellar population is spread across an extended network of molecular clouds. It contains hundreds of pre-main sequence stars, including many T Tauri stars, but relatively few massive O and B stars. That makes Taurus very different from a place such as Orion. In Orion, massive stars dominate the central environment. The trapezium stars produce intense ultraviolet radiation and actively erode nearby material. Taurus is quieter in that particular sense. It still contains jets, outflows, disks, magnetic activity, collapsing cloud cores, and all the other processes expected from young stars, but the region lacks a large concentration of extremely massive stars dominating the entire environment. That difference makes Taurus Auriga extremely valuable. Researchers can study the formation of stars similar in mass to the Sun, without the surrounding region being strongly influenced by a nearby population of O stars. The cloud structure is also extended. Young stars do not occupy one compact spherical cluster. They are distributed along molecular filaments and in smaller groups across the larger cloud complex. This is exactly the kind of structure that has changed how astronomers think about stellar associations. A large association does not necessarily begin as a dense cluster and then expand into a loose one. Some begin loose. Stars follow the structure of the gas. Dense pockets produce small groups. Filaments produce strings of young objects. Several related sites of formation can operate across a molecular cloud at the same time. Taurus gives us a nearby view of that process. T Tauri stars themselves come in different observational categories. Classical T Tauri stars are still actively accreting substantial material from circumstellar disks. Gas moving from a disk onto the star produces characteristic emission features, especially strong hydrogen emission. Weak-line T Tauri stars show much less evidence of active accretion. Some have already lost much of their inner disk. Both kinds are young. They simply represent different disk and accretion conditions within the pre-main sequence population. This means a T association can help astronomers study how quickly disks change. Within one broad young population, some stars have thick disks, some have thinner disks, some show inner holes, Some have almost no detectable disk left. Planets may already be forming inside these systems, while the surrounding association is still young enough that many of its stars have not reached the main sequence. That overlap is important. Star formation and planet formation are not completely separate stages in which nature finishes one task, takes a break, and begins the other. Planetary systems begin developing while their host stars are still young. A T association allows us to study both processes at once. Another example, often included among T associations, is the TW Hydrae association, or TWA. It is much closer to the Sun than most active molecular cloud complexes, and contains a relatively small population of young stars. TW Hydrae itself is particularly famous because it hosts a nearly face-on protoplanetary disk that has been studied in extraordinary detail. The wider association is several million years old, and no longer sits inside a large obvious molecular cloud. That makes TWA useful as a slightly later stage than regions where T Tauri stars remain deeply connected to active cloud material. By comparing places such as Taurus Auriga with older young associations, astronomers can watch the environmental context disappear. First, young stars form among dense clouds. Then feedback and ordinary cloud evolution remove the surrounding gas. The stars spread. Disks evolve. Eventually, the association begins to resemble a moving group more than an active star-forming region. Before getting there, however, there is another historical association type tied directly to the dust that remains around young stars. These are R associations. The R stands for reflection. A reflection nebula is a cloud of dust that becomes visible because nearby stars illuminate it. Unlike an emission nebula, where ultraviolet radiation ionizes gas and causes that gas to emit its own characteristic light, a reflection nebula primarily shines by scattering starlight. Blue wavelengths tend to scatter efficiently, so reflection nebulae often appear blue in visible light images. The principle is not completely unlike the reason Earth's sky appears blue, although the physical environment is obviously quite different, and there is considerably less concern about whether it might rain. An R association is a young stellar association connected with a group of reflection nebulae. The classification was introduced by astronomer Sidney van den Berg in the 1960s. These regions contain young stars, often of low or intermediate mass, that remain close enough to their natal dust clouds for scattered light to reveal the relationship. R associations are therefore particularly useful for identifying young stellar populations that do not contain enough extremely hot stars to create the large, bright ionized nebulae associated with major OB complexes. The dust is illuminated rather than completely ionized. One of the best-known examples is Monoceros, R2, usually shortened to MonR2. The name itself preserves the classification. Monoceros is the constellation. R indicates an association connected with reflection nebulae. The number 2 identifies the particular association catalogued in that direction. MonR2 lies roughly 830 parsecs, or around 2,700 light-years, from the Sun. Visible observations show a long sequence of reflection nebulae extending across the region. Those illuminated patches are only the visible portions of a much larger molecular cloud complex. Within the cloud, star formation is still active. MonR2 contains an embedded central cluster with hundreds of young stars, along with dense molecular gas, infrared sources, outflows, and an ultra-compact H2 region produced by massive young stars. At first, that may sound like it belongs in the embedded cluster discussion rather than here. It does. The categories overlap. MonR2 is simultaneously a molecular cloud complex, a star-forming region, a site containing an embedded cluster, and the namesake of an R association. Astronomers classify objects according to the particular feature being discussed. There is no cosmic registration office insisting that MonR2 choose one category and remain there. The reflection nebulae trace places where young stars illuminate nearby dust. Infrared observations reveal stars hidden deeper within the cloud. Radio observations detect ionized gas and molecular material. X-rays can identify active young stars. Millimeter observations trace coal dust and molecules. Each wavelength adds another population or physical process to the same region. The R association label comes from what was historically noticeable in visible photographs. Modern multi-wavelength astronomy shows that the underlying environment is much richer. This is also true of OB and T associations. The three terms are helpful, but they should not be mistaken for rigid evolutionary stages. A young star-forming complex could contain an OB association because massive stars are present. The same region could contain many T Tauri stars. Parts of its remaining dust could form reflection nebulae. Compact bound clusters might exist within the larger unbound association. Several smaller groups could be forming at slightly different times. Later, the gas disappears, and much of the population becomes a broad-moving group. Classification depends partly on scale. Zoom in on the Orion Nebula, and you can talk about the Orion Nebula cluster. Zoom out, and you are dealing with a wider young stellar population inside Orion OB1. Zoom farther out, and you encounter the entire Orion star-forming complex, including molecular clouds, older populations, and related structures. The object has not changed, our question has. The same problem appears when deciding whether an association is gravitationally bound. A large association may be unbound overall while containing smaller subgroups that are locally bound. One part could survive as an open cluster, another part could expand into the galactic field. Several groups might merge, others might separate. Calling the entire region unbound does not mean every pair of stars is immediately leaving every other star. It means the gravitational energy of the larger population is not sufficient to preserve the complete system as one long-lived cluster. Its future members are field stars. We can estimate how that future unfolds by measuring their present velocities. Suppose two subgroups are separated by several dozen light-years and moving apart by a few kilometers per second. A few kilometers per second sounds slow because we are used to roads, trains, and aircraft. Give that velocity 10 million years, the separation becomes enormous. A star moving at only 1 kilometer per second travels a little more than 1 parsec, about 3.26 light-years, in roughly 1 million years. At 5 kilometers per second, it covers more than 16 light-years in the same period. Continue for tens of millions of years and a recognizable association becomes a wide population spread through the galactic disk. Nothing dramatic needs to happen. The stars simply keep moving. That is why age is so important when identifying associations. A loose group of 10-million-year-old stars can still preserve a coherent pattern. Wait several 100 million years, and galactic rotation, molecular cloud encounters, spiral structure, and gravitational interactions have had much longer to rearrange them. Eventually, shared position becomes nearly useless. Shared velocity can remain informative for longer, although even that record gradually becomes harder to interpret. Chemistry can provide another clue because stars born from related material may have similar elemental abundances. Combining chemistry with motion, age, and orbital reconstruction gives astronomers a way to search for stellar relatives after the original association has become difficult to see. The Sun may once have belonged to exactly this kind of environment. We know it formed from a molecular cloud about 4.6 billion years ago. It almost certainly formed near other stars. Whether that population would best be described as a cluster, an association, or part of a more complex hierarchical star-forming region is much harder to determine after so much time. Any nearby massive stars from that environment disappeared billions of years ago. Lower mass siblings could still exist. They are simply mixed into the Milky Way. A star born beside the Sun might now be thousands of light-years away. Another might pass relatively close to the solar system without us recognizing the relationship. 4.5 billion years is ample time to lose touch with the family. Young associations let us see the process before the information has been erased. SCOSEN shows an enormous OB population already divided into expanding subgroups. Orion OB1 shows that a famous star-forming region contains many overlapping populations rather than one simple cluster. Taurus Auriga shows low-mass star formation distributed through molecular clouds without a dominating population of massive O-stars. TW Hydrae shows what a young low-mass population can look like after much of the original cloud has disappeared. Monoceros R2 shows young stars still illuminating and interacting with the dusty material surrounding them, while embedded populations continue forming inside the same complex. Viewed together, O, B, T and R associations are not just three labels. They are different observational windows into the period when stars have formed together but have not settled into a permanently bound system. Some are easy to identify because massive stars are extremely luminous. Some reveal themselves through hundreds of low-mass pre-main sequence stars. Others stand out because their stars illuminate the remaining dust. In every case, the group is temporary. Once a stellar association has expanded far enough, its members may no longer look like a group at all. The stars can be scattered across a large part of the sky, separated by dozens or hundreds of light years, with unrelated stars sitting between them. Nothing obvious in an ordinary photograph tells you that they once formed together. Motion can. If several stars have similar ages, compatible chemical compositions, and closely related velocities through the Milky Way, astronomers can sometimes reconstruct a common origin even after the original cluster or association has nearly disappeared. Groups identified this way are often called moving groups. The basic idea is straightforward. Stars formed together begin with related positions and velocities. Once the original system disperses, each star continues orbiting the centre of the Milky Way. Their paths slowly separate, but for a while their motions can remain similar enough that the relationship is detectable. It is a little like watching a group of cyclists after they leave a starting line. At first, they are packed together. Later, they spread along the road. Eventually, some are far ahead and others behind, but if you can measure their direction and speed, you may still recognise that they are following the same route. Stars receive the considerably larger version of that road, with one inconvenient addition. The road itself has gravity. The Milky Way's disk, bulge, spiral structure, molecular clouds, central bar, halo, and dark matter all influence stellar orbits. Over time, those forces alter the motions of stars that began together. A young moving group is therefore much easier to reconstruct than a population dispersed several billion years ago. One of the most studied nearby examples is the Beta Pictoris moving group. Its name comes from Beta Pictoris, a bright young star about 63 light-years from Earth in the southern constellation Pictor. Beta Pictoris became famous long before the moving group surrounding it was fully understood because the star has a prominent debris disk. The disk was imaged in the 1980s, making Beta Pictoris one of the earliest stars around which astronomers directly saw a large dusty disk. We now know that the system also contains planets. Beta Pictoris b is a massive gas giant directly imaged orbiting the star, and Beta Pictoris c was later detected through measurements of the star's motion. The star itself is only part of the larger story. Across the solar neighbourhood, astronomers identified other young stars moving through the Milky Way with velocities related to Beta Pictoris. These stars are spread over a substantial volume rather than gathered into an obvious cluster. Together they form the Beta Pictoris moving group, often shortened to BPMG. Its age is young enough that many members still carry obvious signs of recent formation. Researchers generally place the group in the neighbourhood of 20 million years old, although different dating methods give somewhat different results. A widely used age based on stellar evolution and lithium depletion is around 23 or 24 million years. Kinematic studies that attempt to trace the stars backward have produced estimates closer to 16 to 19 million years in some analyses. That disagreement is useful rather than embarrassing. A moving group gives astronomers several different clocks to compare. One method looks at the positions of stars on stellar evolution diagrams. Another examines lithium in low-mass stars. Lithium is gradually destroyed inside many stars as material reaches temperatures high enough for nuclear reactions. The rate depends on stellar mass, so a population's lithium pattern can help determine its age. A third method uses motion. Measure the three-dimensional velocities of group members, calculate their paths backward through the gravitational field of the Milky Way, and ask whether they occupied a smaller volume in the past. In principle, this should reveal when the group was most compact. In practice, small errors in distance or velocity become increasingly important as the calculation is extended millions of years backward. Binary stars complicate radial velocity measurements. The exact model of the Milky Way's gravitational field matters. The group may also have formed with some spatial extent rather than at one precise point. Tracing stellar history backward is less like rewinding a perfect recording and more like trying to reconstruct where several hundred leaves entered a river after watching them downstream. You can do quite a lot. You should not expect every leaf to return to one exact twig. Beta Pictoris is especially valuable because its members are close enough for detailed observations of disks and planets. Young planets are still warm from formation and can emit substantial infrared radiation, making some of them easier to detect directly than older planets of similar mass. If the host star belongs to a moving group with a reasonably well-constrained age, astronomers gain an approximate age for the planet too. That is extremely useful because a young giant planet's brightness depends on both its mass and its age. A luminous object might be relatively massive, or it might simply be very young. Knowing that the surrounding stellar population formed roughly 20 million years ago removes part of that uncertainty. Moving groups have therefore become important hunting grounds for directly imaged exoplanets. Another familiar nearby population is the AB Doradus moving group. It takes its name from AB Doradus, a rapidly rotating young star system about 49 light-year away. The group is considerably older than Beta Pictoris. Age estimates commonly place AB Doradus at around 100 to 150 million years old, with values near 150 million years often used in modern work. By that age, the original star-forming cloud has long disappeared. Any obvious young cluster structure has also been greatly reduced. The stars are distributed across the solar neighbourhood. What identifies them is the combination of their youth and related space motion. Even here, membership is not always obvious. Lists of candidate members change as measurements improve. A star may have the correct motion but the wrong age. Another may appear young but travel at a velocity inconsistent with the group. A binary system can produce misleading radial velocities. An apparently good candidate can disappear from the membership list after one better measurement. Moving group astronomy occasionally resembles a family reunion, where several guests have been asked to bring identification. Gaia has made this work far more powerful. To understand why, consider what astronomers actually need to measure. A star's location on the sky provides two coordinates. Parallax gives distance. Proper motion gives movement across the sky. Spectroscopy can provide radial velocity, showing how quickly the star moves toward or away from us. Combine those measurements, and astronomers can estimate the star's six-dimensional phase space position. 3 dimensions describing where it is, and 3 describing how it is moving. For a single star, that information describes an orbit. For millions or billions of stars, patterns begin appearing. Gaia has measured positions and motions for an enormous fraction of the stars visible throughout the Milky Way. The mission has surveyed nearly 2 billion sources, allowing stellar populations to be separated in ways that were nearly impossible when astronomers relied mainly on photographs and smaller catalogues. A loose family that disappears against the background of the sky can stand out when the motions are plotted. But there is a complication. Stars moving similarly do not always share a birthplace. This is one of the reasons the term moving group needs care. The Milky Way can create groups of stars with similar velocities through gravitational dynamics alone. The central bar and spiral structure can affect stellar orbits and produce concentrations in velocity space. These stars may have very different ages and chemical compositions. They did not form together. They simply ended up responding in similar ways to the galaxy's gravitational structure. The Hercules stream is a famous example. Despite the word stream, it is not thought to be the remains of one dissolved star cluster. It contains stars with a broad range of ages and compositions. Its unusual motion is associated with dynamical effects in the Milky Way, particularly those related to the galactic bar. That gives us two very different uses of similar language. A young moving group such as Beta Pictoris can represent a genuine stellar family. A dynamical moving group such as the Hercules stream can contain unrelated stars brought into similar orbital behavior by the galaxy. Astronomers separate these possibilities by checking more than velocity. Age matters. Chemical composition matters. The distribution of stars in space matters. The orbit matters. A group containing stars with ages ranging from several 100 million to 10 billion years is not likely to have formed in one nursery. Once we leave the galactic disk and move into the halo, another type of structure becomes especially important: stellar streams. A stellar stream is an elongated population of stars following a related orbit around the galaxy. Some streams are enormous remnants of disrupted dwarf galaxies. Others are much narrower and formed from globular clusters that lost stars through tidal forces. The second type gives us a particularly clear view of a star cluster being stretched into the Milky Way. A globular cluster orbiting our galaxy constantly feels the difference between its own gravity and the gravitational pull of the Milky Way. Stars near the outskirts of the cluster are weakly bound. Some escape through gravitational interactions inside the cluster. Others are removed by tidal forces. They do not simply scatter in random directions. Because the escaped stars retain orbital velocities similar to the cluster itself, they tend to spread along the cluster's orbit. Some move slightly ahead. Others fall slightly behind. Over many orbits, these escaping members produce two extended tidal tails. The central cluster remains visible for a while, with a long stream of former members stretching away on either side. Palomar 5 provides one of the clearest examples. Palomar 5, usually called PAL 5, is a sparse globular cluster in the Milky Way's halo. It lies roughly 67,000 light-years from the Sun. Compared with famous globular clusters such as Omega Centauri or 47 Tucanae, Palomar 5 is not especially impressive as a compact object. That is partly because the Milky Way is taking it apart. Observations from the Sloan Digital Sky Survey revealed long tidal tails extending away from the cluster. Later studies trace PAL 5's debris across an even larger region of the sky, with the known stream extending roughly 20 degrees. At PAL 5's distance, that corresponds to thousands of light-years of stellar debris. The cluster at the centre is therefore only the surviving portion of a much larger structure. Many of the stars that once belonged to PAL 5 now occupy its tidal stream. If we could somehow accelerate the process and watch millions of years pass in a few minutes, the cluster would gradually lose members into these tails. The tails would lengthen, the central population would shrink. Eventually PAL 5 could disappear as a recognizable cluster, leaving its stars spread along the orbit. The cluster would be gone, its trajectory would remain written across the halo. The reason streams become so long is the orbital difference between escaped stars. Suppose a star leaves the cluster with slightly more orbital energy than the cluster itself. Its galactic orbit changes a little. Another star escapes with slightly less. Its orbit changes in the opposite direction. The difference is small at first. After hundreds of millions of years, the stars can be separated by enormous distances while still occupying related orbits. This process produces an exceptionally thin structure compared with the broad stellar populations created by disrupted dwarf galaxies. A globular cluster is compact and dynamically cold, meaning its stars begin with relatively small velocity differences. Its stream can therefore remain narrow. A dwarf galaxy is larger and has a greater internal spread in velocities. When disrupted, it tends to produce a broader structure. That distinction is extremely useful. A thin stream acts as a sensitive tracer of the gravitational field it moves through. Palomar 5 has been used for exactly that purpose. The shape and motion of its tidal tails depend on the Milky Way's gravity. Researchers can construct different models for the distribution of matter in the galaxy, calculate how a PAL 5-like cluster and its escaping stars would move, and compare the result with the observed stream. This provides information about the mass of the Milky Way, including the dark matter that cannot be seen directly. The stars are effectively test particles moving through a gravitational field. We see the stars, we infer the gravity. From the gravity, we estimate where the mass must be. A cluster being destroyed therefore becomes a measuring instrument. It is an unfortunate career change for the cluster, but a useful one for astronomy. PAL 5 still has an identifiable progenitor. Another famous stream shows what happens after even that disappears. GD1 is a very narrow stellar stream in the Milky Way's halo. It was discovered in Sloan Digital Sky Survey data, and later mapped in much greater detail using Gaia and other surveys. The stream extends across roughly 100 degrees of the sky. Its stars are old and metal poor, and the stream's narrowness strongly indicates that its progenitor was a globular cluster rather than a dwarf galaxy. There is one obvious difference between GD1 and PAL 5. We can still point to PAL 5. There is no similarly obvious surviving cluster sitting inside GD1. The progenitor appears to have been completely, or almost completely, disrupted. This is a stellar stream without a visible parent cluster. Models suggest that the cluster responsible for GD1 may have dissolved hundreds of millions or even billions of years ago. The stars remained. The cluster did not. That makes GD1 particularly useful when thinking about how many globular clusters the Milky Way once contained. We see roughly 150 globular clusters around our galaxy today. Those are survivors. Streams such as GD1 demonstrate that other clusters existed and have since been destroyed. The current globular cluster population is therefore not a complete inventory of everything the Milky Way ever formed or acquired. Some clusters have been dismantled into the halo. Their stars may remain coherent enough to detect as streams for a long time. Eventually, even those streams become mixed into the larger stellar population. GD1 also contains irregularities. A perfectly undisturbed thin stream would have a relatively smooth distribution of stars along its length. GD1 does not. Astronomers have identified gaps and an unusual offshoot commonly called a spur. One explanation is that something massive passed near the stream and disturbed it. A normal star would usually be too small to produce a feature of the observed scale. Researchers have considered encounters with objects such as giant molecular clouds, globular clusters, or concentrations of dark matter. One particularly interesting possibility is a dark matter subhalo. In standard models of cosmology, the Milky Way's dark matter halo should contain smaller concentrations of dark matter, many of which may contain little or no visible matter. A dark subhalo could therefore pass through a stellar stream without providing a bright object to blame afterward. The stars would move. Nothing obvious would be sitting nearby. Astronomers could then use the disturbance to infer that an unseen mass had passed through. This is why very narrow streams are sometimes described as gravitational detectors. Their stars began on closely related orbits. Disturb that arrangement, and the change can persist. A gap might indicate that stars were pulled away from one part of the stream. A spur could contain stars deflected from the main track. Changes in velocity can provide additional evidence. The difficulty is that the Milky Way contains plenty of ordinary objects capable of disturbing stellar orbits too. The galactic bar matters. Spiral structure matters. Molecular clouds matter, especially for streams passing through the disk. Known globular clusters and satellite galaxies can produce encounters. Astronomers therefore cannot observe one gap and immediately announce that dark matter has been caught interfering with traffic. They model the orbit, reconstruct possible encounters, and compare alternatives. The fact that streams respond to so many gravitational influences is both the reason they are useful and the reason they are complicated. Another important stream connected to a surviving globular cluster comes from NGC 5466. NGC 5466 is an old metal-poor globular cluster in the Milky Way's halo, roughly 52,000 light-years away. Observations have identified extended tidal structures associated with it, again showing that the cluster is losing stars as it orbits the galaxy. The exact dimensions and continuity of these features have been refined as surveys improved, but the overall lesson is the same as PAL 5. A globular cluster can look compact when viewed alone while actually being only the densest remaining point inside a much larger disrupted structure. This changes the way we should picture the galactic halo. It is not simply a smooth background containing isolated globular clusters placed here and there. It contains streams, shells, substructures, populations left by accreted dwarf galaxies, debris from globular clusters, stars whose original systems disappeared long ago. Some structures are thin enough to point back to cluster disruption. Others are broad enough to reveal the remains of entire galaxies. Gaia has helped uncover many of them by measuring stellar motions. In 2024, researchers using Gaia data described two ancient stellar structures named Shakti and Shiva. These are not dissolved star clusters like GD1. They represent much larger populations associated with the early assembly history of the Milky Way. Their existence is useful here because it shows how far the idea of identifying a population through motion can be taken. Stars that appear mixed with the rest of the galaxy can still retain common patterns in orbital energy, angular momentum, chemistry, or motion. A physical structure can disappear from ordinary space while surviving in what astronomers call phase space. That phrase sounds more intimidating than necessary. Position space tells us where stars are. Velocity space tells us how they move. Phase space combines both. Two stars can be far apart in position but close in velocity. Two stars can sit next to one another while following completely different orbits. Once both kinds of information are available, hidden structures become visible. This is why astronomers sometimes speak of stellar archaeology. The ancient object may no longer exist. What remains is evidence. A surviving cluster gives one kind, a tidal tail gives another. A chemically distinct population on a common orbit gives another. A narrow stream wrapping around the galaxy gives one of the clearest records of all. There is also an important difference between the fate of a young moving group and that of a globular cluster stream. A young moving group usually formed in the galactic disk. Its stars can be relatively young, chemically enriched, and associated with the recent star formation of the Milky Way. As the group disperses, its members join the disk's field star population. A globular cluster stream can be ancient and metal-poor, moving through the halo on an orbit that may be highly inclined relative to the disk. The two structures can look similar in the sense that neither is a compact cluster. Their histories are entirely different. Beta Pictoris is a young family whose stars have only had a few tens of millions of years to separate. GD1 is debris from an ancient cluster whose disruption has been unfolding over billions of years. One is useful for studying young stars, disks, and planets. The other is useful for studying galactic gravity, dark matter, and the destruction of old stellar systems. Between them lies a broad spectrum of structures at different stages of dispersal. The Hyades, which we encountered earlier as a nearby open cluster, provides a useful bridge. Gaia measurements have revealed extended tidal tails connected to the Hyades, reaching far beyond the familiar central cluster. The stars in those tails are not arranged randomly. They were gradually removed as the cluster interacted with the Milky Way. The Hyades therefore contain several identities at once. It is an open cluster, it has escaping members, it has tidal tails. Some stars traditionally described as part of a wider Hyades-moving population may not all be genuine former cluster members, because galactic dynamics can place unrelated stars into similar velocity patterns. Again, motion alone is not enough. The best candidates should also make sense chemically and chronologically. In a genuine dissolved cluster, the stars should have compatible ages. Their elemental abundances should show the relationships expected from a shared birth environment. Their orbits should be capable of connecting back to a common system. This is where chemical tagging becomes especially attractive. Every star contains a record of the gas from which it formed. Measure enough elements precisely enough, and stars born together may occupy similar regions of chemical space even after their positions and velocities have changed. The idea is powerful. The execution is difficult. Many molecular clouds in the Milky Way can have similar compositions. Stars can alter the abundances visible at their surfaces during evolution. Measurements have uncertainties. Binary interactions can complicate individual stars. A chemical fingerprint is not necessarily as unique as a human fingerprint. Still, chemistry adds another independent line of evidence. Position can fade. Velocity can change. The chemical composition of a long-lived star can preserve part of its origin for billions of years. Combine all three and the chances of finding genuine relatives improve. This gives us a way to think about the eventual fate of almost every cluster we have visited so far. An embedded cluster begins inside gas. The gas clears. A surviving system may appear as an open cluster. The open cluster gradually loses members. Those members form tails, loose populations, and moving groups. The original cluster becomes harder to identify. Eventually its stars join the galactic field. A globular cluster follows a related process on a much longer timescale. It loses stars. Tidal tails form. The central cluster shrinks. If disruption continues far enough, only the stream remains. Later, even that stream becomes mixed into the halo. At no point do the stars vanish, the organization vanishes. That distinction is important because galaxies are built partly from this continuous rearrangement of stellar populations. The Milky Way contains stars that formed in clusters we can still see. It contains stars from clusters that dissolved before the Sun formed. It contains stars stripped from dwarf galaxies. It contains streams whose progenitors are still present, and others whose progenitors have disappeared. It contains moving groups young enough that we can estimate where their members were only a few million years ago. The galaxy is not a collection of stars that were independently placed into orbit. It is a mixture of families whose relationships become harder to recognize with time. Gaia has made those relationships much easier to recover. A star that appears isolated today may turn out to share motion with several dozen young neighbors. A sparse globular cluster may be found sitting between two enormous tidal tails. A line of faint halo stars can reveal the orbit of a cluster that no longer exists. A gap in that line can record a gravitational encounter with something we cannot see. The cluster itself may be gone, but the physical consequences of its existence remain measurable. There is one limit, however. Moving groups and thin streams are usually the products of systems that were already losing their identity. They tell us about dispersal. If ordinary open clusters gradually unravel, what happens when a newborn cluster begins with enough mass to have a serious chance of staying together? This takes us into a category that is less familiar to casual skywatchers, partly because the best examples are often distant, heavily obscured by dust or found in galaxies where star formation is proceeding much more aggressively than it is around the Sun. They're usually called young massive clusters, and at the most extreme end, astronomers often use another term, superstar clusters. There is no single universal mass boundary where an ordinary cluster suddenly receives a certificate announcing that it has become young and massive. The terminology is descriptive. In general, astronomers are talking about young, compact, gravitationally bound systems containing far more stellar mass than a typical open cluster, often tens of thousands of solar masses or more within only a few light years. Superstar clusters push the same idea farther. They can contain hundreds of thousands, and in some cases perhaps millions, of solar masses in stars packed into an extremely small volume. They are bright, compact, full of massive stars, and often associated with periods of unusually intense star formation. The important difference is not simply that someone added more stars. Packing tens of thousands of stars into a small region changes the environment. The gravitational field becomes stronger, the density rises. Massive stars become numerous enough that their winds and radiation can influence the surrounding gas collectively. Supernovae may eventually occur in rapid succession. Binary interactions become more important. Close stellar encounters become less unusual. The cluster can begin affecting its host galaxy instead of merely occupying a small part of it. This is one reason young massive clusters attract so much attention. They let astronomers study what happens when star formation is concentrated close to its practical extremes. The Milky Way still contains several excellent examples. One of the most remarkable is Westerlund 1. Westerlund 1 lies roughly 12,000 light-years away in the direction of the constellation Ara. It is hidden behind enough interstellar dust that it is unimpressive in ordinary visible light, which is almost absurd considering what is actually there. Astronomers estimate that Westerlund 1 contains somewhere around 50,000 to 100,000 times the mass of the Sun. All of that stellar mass is concentrated inside a region less than about 6 light-years across. For comparison, the nearest star system to the Sun, Alpha Centauri, is more than 4 light-years away. Place the solar system near the middle of Westerlund 1, and you would not have one neighbouring stellar system within that sort of distance. You would have an entire crowd. ESA has estimated that if the solar system were located in the heart of Westerlund 1, the sky could contain hundreds of stars appearing roughly as bright as the full moon. Sleeping might become more of an architectural challenge. Fortunately, we are 12,000 light-years away and have curtains. Westerlund 1 is only a few million years old. That short age is immediately obvious from the stars it contains. Its population includes enormous evolved stars that began their lives with high masses. Astronomers have identified red supergiants, yellow hypergiants, luminous blue variables, Wolf-Rayet stars, and many hot massive stars within the same cluster. These are not types of stars that remain around for billions of years. Massive stars evolve quickly because their cores reach high temperatures and consume nuclear fuel at a tremendous rate. A low-mass red dwarf can survive for trillions of years. The Sun can spend roughly 10 billion years on the main sequence. A star tens of times more massive than the Sun may complete its entire life in only a few million years. That means a cluster such as Westerlund 1 gives astronomers a remarkable snapshot. Its stars formed during roughly the same broad period, but because their masses differ, they're already following different evolutionary paths. Some remain hot and blue, some have expanded into supergiants, some are losing material through powerful stellar winds. The most massive members are approaching or may already have reached the stages that lead to core collapse supernovae. Westerlund 1 even contains a magnetar known as CXOUJ 16471.2-455216. A magnetar is a type of neutron star with an extraordinarily strong magnetic field. Neutron stars are the compact remnants left behind after some massive stars undergo supernova explosions. Finding one inside such a young cluster means that at least one star capable of producing a neutron star has already completed its entire evolution, while the cluster itself is only a few million years old. That gives astronomers useful constraints on the masses and evolutionary histories of neutron star progenitors. It also reminds us how quickly the most massive stars work. A human lifetime is barely noticeable to a normal star. To an extremely massive star, a few million years can contain the entire story. Westerlund 1 is particularly valuable because it contains many rare massive star types, at essentially the same distance and with related ages. Usually if you want to compare a red supergiant with a Wolf-Rayet star and a luminous blue variable, you may be studying stars scattered across very different parts of the galaxy. Distances can differ, ages can be uncertain, chemical compositions can vary. Inside one massive cluster, several of those uncertainties become easier to control. The cluster acts as a laboratory for massive stellar evolution. It is also a laboratory for something larger. With so many massive stars concentrated together, their winds combine. Hot stars continuously throw charged particles into space. The fastest winds can reach thousands of kilometers per second. Those winds collide with one another, shock the surrounding gas, produce X-rays, and inject enormous amounts of energy into the cluster environment. Supernova explosions add still more energy. In late 2025, observations from NASA's Fermi Gamma Ray Space Telescope were used to trace a large outflow associated with Westerlund 1, including high-energy particles moving away from the cluster. The result gives astronomers a nearby example of how a concentrated population of massive stars can drive material out into the surrounding galaxy. This is sometimes called stellar feedback. The name sounds gentle. The process is not. Stars form from gas. Then the newborn stars heat the gas, ionize it, push it with winds, and eventually explode inside it. Feedback can prevent some nearby gas from forming additional stars. Under other circumstances, expanding shells can compress gas elsewhere and contribute to new star formation. The outcome depends on geometry, density, timing, and the amount of energy involved. In a massive cluster, these effects overlap. One O star can reshape its immediate surroundings. Dozens or hundreds of massive stars can reshape an entire star-forming complex. A second Milky Way example lies much farther away in the Carina spiral arm. NGC 3603 is about 20,000 light-years from Earth and contains one of the most massive young stellar clusters known in our galaxy. The designation can cause a little confusion because NGC 3603 is used for the broader nebula region, as well as the central starburst cluster within it. At the centre is an extremely dense concentration of young stars. Thousands of stars occupy the region. Some of the most massive stars known in the Milky Way are found there. The surrounding nebula contains gas and dust that show exactly what those stars are doing to their birthplace. Ultraviolet radiation from hot massive stars ionizes hydrogen. Stellar winds push outward. A large cavity has been cleared around the central cluster. Farther away, dense pillars and clouds remain. Some continue forming stars. So NGC 3603 lets astronomers observe two processes at the same time. A massive cluster has already formed. The surrounding molecular material has not finished forming stars. This is useful because the central stars provide an environment much more intense than a quiet region such as Taurus Auriga. A young low-mass star in Taurus forms without dozens of nearby O stars flooding its disk with ultraviolet radiation. A young star near the core of NGC 3603 is not so fortunate. Its circumstellar disk may be irradiated. Nearby winds can affect surrounding material. Close gravitational encounters are more likely. Any forming planetary system develops under conditions very different from those in a sparse stellar association. This raises a larger question about planets in massive clusters. Can planetary systems survive? The answer is not simply yes or no. Planets can form in clusters. We have evidence for planets around stars belonging to various stellar groups. But the probability that a planetary system survives unchanged depends on the density of the environment, the distance between stars, the strength of nearby radiation, and the architecture of the system itself. A planet orbiting very close to its star is difficult for a passing star to disturb. A distant planet on a wide orbit is more vulnerable. A protoplanetary disk can also lose gas when exposed to intense ultraviolet radiation from nearby massive stars. This does not mean every dense cluster is hostile to planets. It means the conditions for building and keeping planetary systems are not identical everywhere. Our solar system formed somewhere between the extremes. There are clues suggesting that massive stars may have existed near the young sun, but the original solar environment was probably not as densely populated as the centres of the most extreme known young clusters. Exactly where our birth environment fits remains uncertain. Clusters such as NGC 3603 and Westerlund 1 give us the upper end of the comparison. Then there is R136. R136 sits at the centre of the giant 30 Doradus star-forming region, better known as the Tarantula Nebula, in the Large Magellanic Cloud. The Large Magellanic Cloud is a neighbouring satellite galaxy of the Milky Way, roughly 160,000 to 170,000 light-years away, depending on the exact distance being used. Even from that distance, 30 Doradus is extraordinary. There is no star-forming region in the Milky Way quite as large and active as the Tarantula Nebula. At its core, R136 contains a dense population of extremely young and extremely massive stars. The cluster is only around 1 or 2 million years old in its central population. That is so young that its most massive stars have generally not yet had time to end their lives as supernovae. Some individual members began with masses well above 100 times the mass of the Sun. R13601, one of its most famous stars, has long been considered among the most massive stars known, although estimates of its exact mass have changed as observations and stellar models improved. This is an important detail whenever extremely massive stars are discussed. A star is too distant for us to place on a scale. Astronomers infer its mass from luminosity, temperature, spectrum, stellar winds, orbital behaviour if a companion is available, and models of how massive stars evolve. At the upper end of the stellar mass range, those models become difficult. Very massive stars lose material rapidly. They can rotate quickly. Many exist in binary or multiple systems. Their winds affect the spectra used to estimate their properties. Even deciding whether a bright source is one star or several closely spaced stars can change the inferred mass dramatically. R136 itself once produced an even more dramatic confusion. Before telescopes could resolve its core properly, astronomers considered whether the central source might contain a single star with several thousand times the mass of the Sun. That would have been a remarkable object. Hubble observations showed that the central region contains many separate stars. The supposed superstar turned out to be a supercluster. Resolving the cluster did not make it less impressive. It simply distributed the impressiveness among more objects. R136 is one of the reasons young massive clusters are sometimes described as possible modern analogues of the environments that created ancient globular clusters. A globular cluster today contains old stars. The gas is gone. The massive stars died billions of years ago. The cluster has undergone enormous dynamical evolution. Its present appearance does not show directly what it looked like when it formed. A cluster such as R136 lets astronomers examine a massive compact stellar system near the beginning of its life instead. That does not mean R136 is guaranteed to become something exactly like a Milky Way globular cluster. The connection is more cautious. If a young massive cluster remains gravitationally bound and survives early gas loss, stellar mass loss, supernovae, internal relaxation, and the tidal field of its host galaxy, then it can evolve into a long-lived massive cluster. After 10 billion years, much of the visible evidence of its youth would be gone. The massive blue stars would be absent, the gas would have disappeared, low-mass stars and stellar remnants would dominate. What started as an extremely luminous blue cluster might resemble an old globular cluster. The challenge is survival. The first tens of millions of years bring major changes. Massive stars lose large quantities of material through winds. Then they explode or collapse into compact remnants. The cluster loses mass. When gravitational mass is removed, the cluster can expand. Some stars escape. The system becomes more vulnerable to the gravitational field of its galaxy. If the cluster began dense and massive enough, it can remain bound. If not, it disperses. Westerlund 1. NGC 3603 and R136 give us nearby laboratories for studying that early period. To see young massive clusters forming on a much larger scale, however, it helps to look at galaxies undergoing collisions. The Antennae galaxies provide one of the best examples. They're catalogued as NGC4038 and NGC4039. The pair lies roughly 65 million light-years away in the constellation Corvus. Each began as a spiral galaxy. For the past few 100 million years, their mutual gravity has been pulling them together. The collision has distorted their disks, thrown long tidal structures outward, compressed gas, and triggered intense star formation. Hubble images show large numbers of bright blue clusters spread through the disturbed galaxies. More than 1,000 young superstar clusters have been identified in the system. This is not because galaxy collisions make stars crash directly into one another. Even when two galaxies pass through each other, individual stars are so small compared with the distances between them that direct stellar collisions remain rare. Gas behaves differently. Gas clouds are extended. When galaxies interact, gravity rearranges those clouds. Gas can be compressed. Shocks can develop. Dense regions accumulate. Star formation can increase dramatically. Instead of making one ordinary cluster here and another there, a major interaction can produce clusters throughout the disturbed gas. Some contain tens of thousands of stars. The most massive may have a realistic chance of surviving for billions of years. Many others will not. That mixture is important. Images of the antennae show numerous brilliant clusters, but brightness is not a guarantee of permanence. Young massive stars produce enormous amounts of light. A cluster can look spectacular while still being gravitationally vulnerable. Over time, the lowest mass systems will tend to disperse. Some will lose stars because of internal dynamics. Others will be disrupted by the changing gravitational field of the merger. The most massive and compact clusters are better candidates for long-term survival. This provides astronomers with an opportunity that does not exist when looking only at ancient globular clusters. We can study a population near birth and ask which systems are likely to remain. How massive were they initially? How quickly did they remove their natal gas? How compact are they? What is the distribution of stellar masses? How much mass do they lose through winds and supernovae? How strong is the tidal field around them? Which clusters remain bound after 100 million years? Which survive 1 billion? Those questions connect star formation today with the globular cluster populations of old galaxies. There is still debate over how directly modern superstar clusters correspond to the formation of ancient globular clusters. The early universe was different from the universe around us now. Galaxies contained larger fractions of gas. Star formation rates were often higher. Chemical abundances were lower. The gravitational conditions inside forming galaxies were different. Ancient globular clusters may have formed through processes that are only partly reproduced in nearby starbursts. But young massive clusters remain the closest observable examples of compact, high-mass stellar systems near the start of their evolution. There are also extreme clusters in the Milky Way, close to the galactic centre. The Arches cluster is one of them. It lies only about 100 light-years in projected distance from the Milky Way's central supermassive black hole, Sagittarius A star. Although the three-dimensional geometry is more complicated than a simple flat map suggests. The Arches cluster is around 2 to 3 million years old. Its mass is on the order of tens of thousands of suns. Within its central regions, the stellar density is extraordinary, making it one of the densest young massive clusters known in the Milky Way. The environment near the galactic centre is already extreme before the cluster is added. Gas is dense and turbulent. Magnetic fields can be strong. Radiation levels are high. The gravitational potential is powerful. Molecular clouds near the centre can contain large amounts of material under pressures much greater than those in the solar neighbourhood. Then, inside that environment, the Arches cluster contains dozens of very massive stars packed together. Infrared astronomy is essential for studying it. Visible light from the cluster is heavily absorbed by dust between us and the galactic centre. Near-infrared observations penetrate much of that obscuration and reveal the stellar population. The Arches also provides a useful test of something called the initial mass function. The initial mass function, or IMF, describes the distribution of stellar masses produced by a star-forming event. Low-mass stars are normally much more common than high-mass stars. For every enormous O star, nature produces many lower-mass stars. Astronomers want to know whether that distribution is universal. Does a molecular cloud near the Sun produce roughly the same proportion of low and high-mass stars as a cloud near the galactic centre? Does a starburst galaxy follow the same pattern? Does very high pressure favour massive stars? Do dense clusters form differently? The Arches cluster has been central to this discussion. Some observations suggested that its mass distribution might be unusually rich in massive stars, sometimes described as top-heavy. Other work has shown that the situation is complicated by mass segregation, stellar evolution, extinction, incomplete detection of faint stars, and the cluster's dynamical history. Massive stars naturally become concentrated toward the centre through gravitational interactions. So if you examine mainly the core, the population can look more top-heavy even if the cluster originally formed with a more ordinary mass distribution. The galactic tidal field also strips stars. Lower mass members in the outer regions can be lost preferentially. A cluster's current mass function is not necessarily its initial mass function. This is a recurring problem when trying to learn how stars formed by observing them after they have spent several million years interacting. The cluster has already edited the evidence. Westerland 1 does the same thing in a different environment, so does NGC 3603. R136 adds different chemical conditions because it belongs to the Large Magellanic Cloud. The antennae add a galaxy merger and widespread starburst activity. By comparing all of them, astronomers can ask whether the physics of clustered star formation changes with environment. Young massive clusters also tell us how galaxies regulate star formation. Imagine a cluster containing hundreds of massive stars. Each produces radiation, each produces winds, some explode. The combined mechanical and radiative energy can carve bubbles through interstellar gas. If enough massive clusters form during a starburst, those bubbles can overlap. Hot gas may escape from the galactic disk. Heavy elements produced by stars can be carried into the halo. Cold gas available for future star formation can be heated or removed. This is how an object only a few light years across can participate in the evolution of a galaxy tens of thousands of light years wide. The cluster does not need to move the entire galaxy itself. It injects energy into the surrounding interstellar medium. Many clusters acting together can produce large-scale outflows. This is particularly important in starburst galaxies, where the rate of star formation is much higher than in the Milky Way today. A galaxy producing stars rapidly also produces massive stars rapidly. Massive stars produce feedback rapidly. The starburst therefore contains its own braking mechanism. Make enough stars, and those stars begin disrupting the material needed to make more. That does not necessarily stop the process immediately. Gas can continue flowing inward. New dense clouds can form. One region can be cleared while another begins collapsing. The result is a complicated competition between gravity, cooling, turbulence, radiation, winds, and supernovae. Superstar clusters are concentrated points where much of that competition becomes observable. They also provide clues about conditions in the early universe. When we look very far away, we look backward in time. Galaxies seen billions of light years away are observed as they were billions of years ago. Many early galaxies appear compact, irregular, and vigorously star-forming. High-resolution observations, increasingly including those from the James Webb Space Telescope, reveal bright clumps that may contain intense clustered star formation. In some early galaxies, a large fraction of the total ultraviolet light can come from compact stellar structures. That raises the possibility that massive clusters were an important mode of star formation when galaxies were young. It may also help explain why old galaxies contain large populations of globular clusters today. The globulars would be the survivors. The disrupted clusters would have contributed their stars to the galaxies around them. This is similar to what happens with ordinary open clusters, only scaled up. A cluster forms, some fraction survives, The rest disperses. The stars do not disappear. They become part of the host galaxy. Over cosmic time, a galaxy can therefore be built partly from stellar systems that no longer exist as recognizable systems. Its smooth background population may contain the dissolved remains of thousands or millions of former clusters. The surviving massive clusters are the exceptions we can still identify. That makes the distinction between a young massive cluster and a superstar cluster less important than the physical questions behind the labels. How much stellar mass formed together? How compact is the system? Is it gravitationally bound? How quickly does it lose gas? How many massive stars does it contain? What happens when those stars begin dying? How much of the cluster survives? And what effect does the cluster have on the galaxy around it? Westerland 1 shows us a dense Milky Way superstar cluster containing 50,000 to 100,000 solar masses and an extraordinary population of massive evolved stars. NGC 3603 shows a young starburst cluster surrounded by a nebula being carved apart by radiation and stellar winds. R136 shows the same basic idea pushed into the much larger 30 Doradus star-forming complex, where some of the most massive stars known are concentrated in an extremely young central system. The Archer's cluster shows how massive star formation operates close to the crowded and highly unusual environment of the galactic center. The antennae galaxies show what happens when a galaxy collision creates compact clusters by the hundreds and thousands. None is simply a larger Pleiades. The environments are different enough that new processes become important. Stellar collisions, while still uncommon in most circumstances, become more plausible in extremely dense cluster cores. Binary interactions are frequent enough to influence the population. Mass segregation occurs rapidly. Massive star winds overlap. Supernova remnants expand into gas already heated by other stars. Compact objects are created in large numbers. Black holes can interact with binaries and with one another. The cluster can expand as stars lose mass. Tidal forces remove outer members. Every stage affects what remains. Give such a system a few billion years, and its appearance may be completely different. The bright massive stars will have vanished. The most spectacular nebular gas will be gone. The cluster may have lost a large fraction of its original mass. If enough of it survives, low-mass stars and stellar remnants will dominate the population. A young cluster that once lit up an entire star-forming region could become a quiet old globular cluster orbiting in a galactic halo. Or it could dissolve entirely and leave no compact system behind. That uncertainty is part of why these young clusters are so useful. We are watching the initial conditions while they still exist. There is one place, however, where extreme stellar crowding does not require a temporary starburst or a young cluster moving through a galactic disk. Nuclear star clusters occupy a very specific address. They sit at or extremely close to the dynamical centers of galaxies, where large amounts of stellar mass can be concentrated into only a few parsecs of space. They are compact, massive, and among the densest stellar systems known. That location changes almost everything about them. A globular cluster can orbit through a galactic halo. An open cluster can drift through the disk. A nuclear star cluster lives at the bottom of the galaxy's gravitational potential, where stars, gas, compact remnants, and sometimes a massive black hole can all accumulate over billions of years. This means a nuclear star cluster does not necessarily contain stars of one age. It may contain ancient stars that have been there for most of the galaxy's history, intermediate age populations formed much later, and young stars produced during comparatively recent episodes of star formation. Instead of representing one main birth event, the cluster can keep growing. Gas can arrive, new stars can form, other star clusters can fall inward. Existing stars age, stellar remnants accumulate. A central black hole may grow at the same time. The result is less like a single stellar family born together and more like a central population assembled through several different routes. Nuclear star clusters are also common. They appear in galaxies across a wide range of types, including spiral galaxies, lenticular systems, and dwarf galaxies. Surveys have shown that these central clusters are especially prevalent in galaxies of intermediate and lower stellar mass, although the exact frequency depends on galaxy type and mass. In the most massive galaxies, the situation changes. Supermassive black holes become increasingly dominant, while recognizable nuclear star clusters become less common. In some galaxies, both exist together. Our own Milky Way is one of those cases. The center of the Milky Way lies roughly 26,000 light-years from us in the direction of Sagittarius. Looking toward it in visible light is frustrating. Large amounts of interstellar dust lie between the solar system and the galactic center, absorbing visible wavelengths so effectively that the central cluster is hidden from ordinary optical view. Infrared observations solve much of that problem. Infrared light passes through the dust more easily, allowing telescopes to reveal the crowded stellar population at the heart of the galaxy. NASA's Hubble Space Telescope has imaged more than 500,000 stars in part of this central region, and that is not the complete population. The Milky Way's nuclear star cluster contains tens of millions of solar masses and stars. Measurements place its total stellar mass in the range of roughly 20 to 40 million times the mass of the Sun, concentrated within only a few parsecs around the galactic center. That is a tremendous amount of matter in a very small region. NASA has offered a useful comparison. The central density can be thought of as cramming roughly 1 million suns into the volume between our solar system and Alpha Centauri. Alpha Centauri is about 4.3 light-years away. In our neighborhood, that volume contains the Sun, the Alpha Centauri system at the far end, and not very much stellar company in between. Near the galactic center, the same sort of volume can contain an enormous stellar population. The night sky from a planet there would be extraordinarily crowded. Whether such a planet would enjoy the arrangement is another question. The Milky Way nuclear star cluster surrounds Sagittarius A star, usually written SGR A star, the supermassive black hole at the center of our galaxy. Sagittarius A star contains about 4 million times the mass of the Sun. That sounds dominant until we compare it with the nuclear star cluster surrounding it. The stars collectively contain several times more mass than the black hole. Very close to Sagittarius A star, however, the black hole's gravity takes control. Several stars orbit so near the black hole that astronomers have tracked their motion over decades. One of the most famous is S2, also called SO-2 in some observing programs. S2 completes an orbit around Sagittarius A star in about 16 years. At its closest approach, it travels at several thousand kilometers per second. Tracking this orbit provided some of the strongest evidence that millions of solar masses are concentrated into an extremely small region. It also allowed astronomers to test predictions from Einstein's general relativity and the gravitational field surrounding a supermassive black hole. So inside one nuclear star cluster, researchers can study ordinary stellar populations, extreme stellar dynamics, black holes, and relativistic gravity without changing targets. The galactic center does tend to make efficient use of telescope time. Most of the stars in the Milky Way's nuclear cluster are old. Studies of the population suggest that a large fraction of its stellar mass formed more than 5 billion years ago. But old does not mean inactive. The central region also contains young stars. Some are only a few million years old. That creates a problem that has occupied astronomers for years. Very close to a supermassive black hole, gravity creates strong tidal forces. A normal molecular cloud approaching the center can be stretched and disrupted before it reaches the density required for ordinary star formation. Yet young massive stars are present there. Some orbit within a fraction of a parsec of Sagittarius A star. So how did they form? One possibility is that gas in the galactic center became concentrated into a sufficiently dense disk around the black hole. If that disk contained enough mass, parts of it could become gravitationally unstable and fragment into stars despite the strong tidal environment. This could explain why some young stars near Sagittarius O star appear arranged in a disk-like orbital structure. Another possibility is that young clusters formed farther from the centre and migrated inward. The difficulty is time. Massive young stars do not live very long. If they formed far away, the cluster containing them would need to reach the centre before the massive stars died. Under some conditions this can happen, particularly if the original cluster is extremely massive and compact, but reproducing the observed population becomes challenging. The stars themselves remain, so the formation mechanism has to explain them. This is one of the advantages of having our own nuclear cluster nearby. In another galaxy, individual stars in the nucleus usually blend together into one bright source. At the Milky Way's centre, astronomers can resolve large numbers of stars and measure their positions and velocities. They can distinguish old red giants from young massive stars. They can follow orbits. They can study metallicities. They can identify stellar disks and search for changes in population with distance from the black hole. The Milky Way becomes a detailed laboratory for processes that are unresolved in most other galactic nuclei. Its nuclear star cluster is not perfectly spherical either. It is flattened along the plane of the Milky Way and shows rotation in the same general direction as the galactic disk. That provides a clue to its history. If a nuclear cluster formed entirely from star clusters arriving on random orbits from every direction, we might expect a more nearly spherical system with little net rotation. A flattened, rotating structure suggests that gas flowing inward through the galaxy and forming stars near the centre has also played an important role. This brings us to the two major ways astronomers think nuclear star clusters can grow. The first is cluster infall. Imagine several ordinary massive star clusters orbiting inside a galaxy. Each cluster moves through a background of stars and dark matter. Its gravity affects the surrounding material, and the response of that material produces a gravitational drag called dynamical friction. Over time, the cluster loses orbital energy. Its orbit shrinks. It moves toward the galactic centre. The closer it gets, the stronger tidal forces become. Eventually the cluster may be partially stripped apart, but its dense central population can survive long enough to reach the nucleus. Repeat this with several clusters and their stars accumulate near the centre. A nuclear star cluster can be built from the remains of other clusters. The process is particularly effective in lower mass galaxies, where dynamical conditions allow massive clusters to sink toward the centre within the age of the universe. This means the nucleus can become a gathering place for clusters that originally formed elsewhere. They begin as separate systems. They orbit the galaxy, they lose energy, they merge near the centre. Their stars become one larger nuclear population. That formation route connects nuclear star clusters directly to the globular clusters we discussed earlier. A globular cluster does not always spend its entire existence orbiting safely in a halo. Under the right circumstances, dynamical friction can gradually bring it inward. The second major growth route is in situ star formation. Here, the stars form inside the galactic nucleus itself. Gas from larger scales in the galaxy loses angular momentum and moves toward the centre. It may be driven inward by bars, spiral structures, interactions with other galaxies, mergers, or instabilities inside the gas. Once enough material accumulates in the central few parsecs, dense clouds can form and produce new stars. Those stars are born directly inside the nuclear cluster. The process can repeat. A burst of star formation consumes some gas. Massive stars produce winds. Supernovae inject energy. The remaining gas may be heated or expelled. Star formation declines. Later, more gas arrives. Another generation appears. Over billions of years, repeated episodes create a population with a wide range of ages and chemical compositions. Modern evidence suggests that both mechanisms operate. The balance appears to depend partly on the mass of the host galaxy. In lower mass systems, the inward migration and merger of star clusters may contribute a larger fraction of the nuclear cluster's mass. In more massive galaxies containing substantial gas flows, repeated star formation near the centre becomes increasingly important. Many real nuclear clusters are probably hybrids. Some of their stars formed elsewhere and migrated inward inside clusters. Others were born at the nucleus, then everything spent billions of years interacting gravitationally. NGC 404 gives us a useful example. NGC 404 is a nearby lenticular galaxy, sometimes called the Ghost of Mirror, because it appears close on the sky to the much brighter star Mirror Andromeda. Its nucleus contains a star cluster with a mass of roughly 10 million suns. Unlike an ancient globular cluster dominated almost entirely by very old stars, the NGC 404 nucleus contains evidence for several populations. Studies have found an old underlying component along with substantial intermediate-age stars, including a large fraction of the nuclear cluster's mass associated with star formation around 1 billion years ago. That history may be connected with a past merger or gas accretion event. Gas entered the central region. Star formation resumed. The nucleus gained another population. NGC 404 may also contain a central black hole in the intermediate mass range, although measuring its mass has been difficult. Different methods have produced different estimates, and separating the gravitational influence of a relatively small black hole from the mass of a dense surrounding star cluster is not easy. This is an important observational problem. In the Milky Way, Sagittarius, a star, is massive enough that stellar orbits close to it clearly reveal its gravitational influence. In a small galaxy, a black hole might contain only tens or hundreds of thousands of solar masses, while sitting inside a nuclear cluster containing millions. The stars themselves then account for much of the central gravity. To detect the black hole, astronomers need extremely precise measurements of how gas or stars move in the innermost region. A nuclear star cluster can therefore both help and hinder the search for black holes. It provides stars whose motions can be measured. It also provides millions of solar masses that must be modelled correctly before any extra invisible mass can be identified. M33, the Triangulum galaxy, shows another useful configuration. M33 is a nearby spiral galaxy in the local group, and it has a bright nuclear star cluster. What it does not have, as far as observations currently show, is a normal supermassive black hole like Sagittarius A star. Measurements of stellar motions in its nucleus have placed very low upper limits on any central massive black hole, compared with those found in the Milky Way or Andromeda. The galaxy still has a dense nucleus. It still has a compact stellar cluster. The large black hole is missing, or at least much smaller than those in the major spiral galaxies around it. That matters because it tells us nuclear star clusters and supermassive black holes are not simply two inseparable parts of the same object. A galaxy can build a nuclear star cluster without building a large central black hole. Another galaxy can have both. In still more massive galaxies, the black hole may become so dominant that the stellar nucleus looks very different. Andromeda, M31 or NGC 224, provides a dramatic example of that last situation. Its central black hole is far more massive than Sagittarius A star. Estimates place it around 100 million solar masses, with some measurements closer to 140 million. The stellar structure surrounding it is unusual enough that early Hubble observations revealed what looked like a double nucleus. For a while, this appeared to mean Andromeda had two separate bright central concentrations. Later work showed that the structure can be explained by stars moving on eccentric orbits around the central black hole. The old stellar population forms an elongated distribution. Stars spend more time near the distant parts of their elongated orbits because they move more slowly there, creating a bright concentration offset from the actual location of the black hole. Inside this older population is a compact disk of young blue stars. Those young stars are no more than a few 100 million years old. That presents the same basic problem seen in the Milky Way, only around a much more massive black hole. How does gas become dense enough to form stars so close to an object whose tidal gravity is capable of disrupting ordinary clouds? Yet the young stars exist. The galactic nucleus has managed it somehow. This is why nuclear star clusters cannot be understood only as dense versions of globular clusters. Their location continually supplies possibilities that an isolated globular cluster does not have. Gas can flow inward from the host galaxy. A central black hole can alter stellar orbits. Fresh star formation can occur. Other clusters can sink toward the center. Galaxy mergers can deliver new material. The nucleus can be rebuilt repeatedly. The environment also changes what happens to compact stellar remnants. Every generation of stars eventually produces remnants. Low and intermediate mass stars leave white dwarfs. Massive stars can produce neutron stars and black holes. In a nuclear star cluster, mass segregation tends to move heavier objects toward the center over long periods. Stellar mass black holes can therefore become concentrated around the supermassive black hole. Neutron stars can occupy the same region. Binary systems encounter other stars and compact objects. Orbits can be altered. Binaries can be broken apart or formed through interactions. A white dwarf can pass another compact object. A neutron star can acquire a companion. Black holes can form binaries and eventually merge. The high density creates possibilities that are extremely rare in the quiet neighborhood around the Sun. One of the most dramatic outcomes occurs when a star passes too close to the central massive black hole. The black hole's gravitational pull is stronger on the near side of the star than on the far side. If that difference becomes large enough, it exceeds the star's own gravity. The star is torn apart. Astronomers call this a tidal disruption event. Part of the stellar material can escape. Part can fall toward the black hole, heating to high temperatures and producing a powerful flare. For a galaxy whose central black hole is normally faint, a tidal disruption event can suddenly make the nucleus brighten dramatically. Nuclear star clusters increase the supply of stars moving through the central gravitational environment, so understanding their density and orbital distribution helps researchers estimate how often these events should occur. Compact objects create another possibility. A stellar mass black hole orbiting inside a nuclear cluster may gradually approach the central supermassive black hole. If the smaller black hole becomes tightly bound, it can lose orbital energy through gravitational radiation and spiral inward. This kind of system is known as an extreme mass ratio in spiral, usually shortened to EMRI. The name describes the situation rather accurately. One object might contain 10 solar masses, the other might contain 1 million. The smaller black hole completes huge numbers of orbits while slowly descending toward the larger one. The gravitational waves produced by such a system carry detailed information about the geometry of space-time around the supermassive black hole. Future space-based gravitational wave observatories are expected to search for signals of this kind. Nuclear star clusters may therefore become important laboratories for gravitational wave astronomy, not because the stars themselves are especially noisy, but because they concentrate compact objects near massive black holes. The same density creates a question about stellar collisions. Ordinary stars almost never collide in the solar neighborhood. The distances are simply too large. Even in most globular clusters, direct collisions remain uncommon. Near the center of a sufficiently dense nuclear cluster, the probability rises. Red giant stars are particularly large targets. Interactions can strip their extended outer envelopes. Collisions, binary exchanges, and close gravitational encounters can gradually alter the population close to the galactic center. Astronomers have long studied the apparent shortage of certain bright red giants in the innermost region of the Milky Way, and considered whether collisions, tidal interactions, stellar evolution, observational effects, or combinations of several processes might explain the distribution. The center is dense enough that mechanisms normally treated as exotic become relevant. Yet nuclear star clusters are not just collections of unusual stellar accidents. Most of their stars spend most of their lives behaving like stars elsewhere. They fuse hydrogen, they evolve, they become giants, they lose mass, they leave remnants. The difference is that all of this happens inside a deeper gravitational environment with far more opportunities for interactions and repeated star formation. Over time, the nucleus keeps a record of the galaxy around it. A young stellar population can indicate that gas reached the centre recently. Multiple metallicities can reveal separate formation episodes. Rotation can preserve evidence for gas inflow. Old populations can preserve stars deposited by ancient clusters. A central black hole records another part of the same history. The nuclear cluster and black hole can grow together, compete for material, and influence one another without following one simple universal pattern. M33 shows a strong nuclear stellar system without a detected supermassive black hole. The Milky Way shows a massive nuclear cluster surrounding a 4 million solar mass black hole. M31 shows a nucleus where a roughly 100 million solar mass black hole dominates the central dynamics. NGC 404 occupies a lower mass regime where a dense nuclear cluster may coexist with a much smaller black hole. These are not 4 steps on one exact evolutionary ladder. They're examples of the range of outcomes galaxies can produce. That range also helps explain why the border between a nuclear star cluster and some other compact stellar systems becomes difficult to define. Suppose a small galaxy contains a dense nuclear cluster, then the galaxy falls into a much larger galaxy. Tidal forces begin stripping away the outer stars. The smaller galaxy loses its disk or halo. More material disappears with each orbit. Eventually, almost nothing remains except the dense nucleus. What should we call it now? It was once clearly a nuclear star cluster because it occupied the centre of a galaxy. After the surrounding galaxy is stripped away, it may look like an unusually massive globular cluster, or it may resemble an ultra-compact dwarf galaxy. Omega Centauri has been discussed as a possible example of such a stripped nucleus. M54, catalogued as NGC6715, provides another important case because it sits at the centre of the Sagittarius dwarf galaxy, which is itself being disrupted by the Milky Way. The distinction between star cluster, galactic nucleus, and compact galaxy can therefore depend on an object's history as much as its present appearance. So far, most of the stellar groups we have encountered have at least had the courtesy to resemble the category assigned to them. An open cluster is loose. A globular cluster is dense and roughly spherical. A stellar association is spread out and unbound. A nuclear cluster sits at the centre of a galaxy. Then, astronomers began finding objects that seemed determined to occupy the spaces between these definitions. Some contained the stellar populations of globular clusters, but were much larger. Others were old and faint but unusually extended. Still others were so massive and compact that astronomers could reasonably argue about whether they were star clusters or galaxies. These objects are not errors in the classification system. They are reminders that nature does not produce stellar systems by selecting a category from a menu. Mass, density, environment, orbit, age, chemical composition, and formation history can vary continuously. The names come afterward. A useful place to begin is with extended star clusters. Ordinary globular clusters are compact. Their half-light radii, meaning the radius containing half of the total light, are commonly only a few parsecs. Extended clusters can be much larger, while still possessing other properties that resemble globular clusters. Several important examples were discovered in the outer halo of the Andromeda Galaxy, M31. One of these is known simply as EC4. The name stands for Extended Cluster 4, which may not be especially imaginative, but it does make filing the observing proposal considerably easier. EC4 lies in the halo of Andromeda, far from the bright inner disk. It was discovered as part of surveys mapping the outer regions of M31, where astronomers were searching for globular clusters, tidal debris, and remnants of smaller galaxies that had interacted with Andromeda. At first glance, EC4 looked unusual because it was too large and diffuse for a typical globular cluster. It was clearly a concentrated stellar system. It was simply spread over more space than expected. Spectroscopic observations using the Keck telescope later measured the velocities and chemical properties of candidate member stars. The results showed a metal-poor population, with an iron abundance well below that of the Sun. Its internal velocity dispersion was small. That matters because velocity dispersion tells astronomers how quickly stars are moving relative to one another inside a system. If a small, faint object contains a large amount of unseen dark matter, its stars should generally move more rapidly than visible stellar mass alone would predict. Dwarf galaxies provide many examples of this. Some contain relatively few stars but have stellar motions indicating much more gravitational mass than those stars can account for. EC4 did not clearly show that behaviour. Within the considerable uncertainty of the measurements, its mass-to-light ratio was consistent with an extended globular cluster rather than a dark matter-dominated dwarf galaxy. So EC4 appears to sit on the star cluster side of the boundary. Its location makes the story more interesting. EC4 overlaps stellar structures in Andromeda's halo, including a component known as stream CP. The cluster and stream have similar velocities and similar metallicities. That suggests EC4 may be associated with the same disrupted system that produced the stream. Perhaps the cluster originally belonged to a smaller galaxy that was later torn apart by Andromeda. The galaxy vanished as a recognizable object. Its debris became part of M31's halo. The cluster survived. This offers one explanation for why large extended clusters are often found in outer galactic environments. Weak tidal fields are kinder to diffuse systems. A compact cluster can survive strong gravitational tides because its stars are held tightly together. A large, low-density cluster is more vulnerable. Place it deep inside a massive galaxy, and stars near its outer regions can be stripped away efficiently. Place the same cluster far into the halo, where the galactic tidal field is weaker and it can remain extended for much longer. Computer simulations have shown that extended clusters can survive naturally in weak tidal environments. The same work suggests that extended clusters in the outskirts of large galaxies may sometimes have been accreted from smaller galaxies. That fits nicely with what we know about galaxy formation. Large galaxies grow partly by absorbing small ones. Those smaller galaxies bring stars, gas, dark matter, and star clusters with them. When the satellite galaxy is disrupted, some of its clusters remain behind. A cluster we observe today in the halo of Andromeda may therefore have spent much of its earlier life inside another galaxy. This is a recurring problem when classifying ancient stellar systems. Their current address is not necessarily their birthplace. Another group of unusual objects carries one of the more memorable names in star cluster astronomy. Faint fuzzies. That is the actual term. Astronomers occasionally resist the urge to name everything with a combination of letters and numbers. Faint fuzzy clusters were identified prominently in the lenticular galaxy NGC1023. NGC1023 lies tens of millions of light-years away and contains an ordinary population of globular clusters, including the familiar compact blue and red populations often seen around large galaxies. Hubble observations revealed something else. Some clusters were faint. They were red. They were larger than typical globular clusters. Their effective radii reached roughly 7 to 15 parsecs, with some studies extending the range closer to 20 parsecs. That is several times larger than an ordinary compact globular cluster. They were also associated strongly with the disk of NGC1023. That last point became extremely important. If faint fuzzies were ordinary halo globular clusters that happened to be unusually large, their motion should resemble the spheroidal population of the galaxy. Instead, observations showed that they rotate with the stellar disk. They belong dynamically to the disk. Their chemistry also differs from what we might expect from ancient metal-poor halo globulars. The NGC1023 faint fuzzies are relatively metal-rich. Recent spectroscopy has added more detail. a 2025 study confirmed several genuine faint fuzzy clusters in NGC 1023 and found ages around 7 to 9 billion years for the measured objects. That makes them old, but generally younger than the galaxy's classical globular clusters, many of which are older than 10 billion years. They have therefore spent an enormous amount of time inside a galactic disk while remaining unusually extended. That requires an explanation. Disks are not necessarily gentle places for star clusters. Molecular clouds can pass nearby. Spiral structures alter gravitational forces. The general tidal field works continuously. Yet these large clusters survived for billions of years. Several formation ideas have been proposed. One possibility begins with groups of young star clusters forming close together. We have already seen that intense star formation can produce entire cluster complexes rather than one isolated system. If several clusters within such a complex merge gravitationally, they can produce one larger remnant. The resulting object can be more extended than an ordinary globular cluster. Simulations have shown that such merged systems can develop properties similar to the faint fuzzies in NGC 1023 and remain stable for billions of years. Another interpretation treats faint fuzzies more like surviving descendants of disk star clusters. Their kinematics strongly tie them to the disk, and some work has argued that they may effectively be old, unusually extended remnants of open cluster-like systems whose particular orbits and structures allowed them to survive. The two ideas are not necessarily incompatible in every galaxy. There may be more than one route to producing an old extended cluster. That is going to become a familiar answer. The universe is quite fond of producing similar-looking objects through different histories. A compact stellar system can form directly as a massive cluster, or it can be the nucleus of a larger galaxy after the outer galaxy is removed. An extended cluster can form large, or it can expand, or it can be assembled through mergers of smaller clusters. Classification from appearance alone becomes risky. Faint fuzzies also reveal an observational problem. They are difficult to find. They are faint and have low surface brightness. In a lenticular galaxy such as NGC 1023, the disk can be relatively smooth, making extended clusters easier to identify. In a spiral galaxy filled with dust, star-forming regions, young clusters, and bright structured arms, the same kind of faint diffuse cluster could be much harder to notice. So their apparent preference for lenticular galaxies may partly reflect where we can detect them most easily. Astronomers have found similar extended systems in several other galaxies, showing that NGC 1023 is not alone. Once again, better observations expand the category. The next objects push the problem much farther. Ultra-compact dwarfs, usually shortened to UCDs, occupy territory between massive star clusters and small galaxies. They were recognized as a distinct population around the turn of the 21st century, especially in surveys of the Fornax galaxy cluster. The discovery was partly accidental. Astronomers conducting spectroscopic surveys found compact objects that looked almost like stars in ground-based images, but their spectra showed that they were not foreground stars in the Milky Way. They belonged to the distant Fornax cluster. They were too luminous to be normal globular clusters. At the same time, they were far smaller than ordinary dwarf galaxies, hence the name ultra-compact dwarf. Early examples had sizes below a few tens of parsecs, but luminosities well above normal galactic globular clusters. As more objects were discovered, the known range expanded. Some UCDs are only somewhat more massive than the largest globular clusters. Others contain tens or hundreds of millions of solar masses. That overlap creates the central question: what are they? There is no single answer that works for all of them. Some UCDs may simply be the extreme upper end of the star cluster population. Imagine an exceptionally massive young cluster formed during a galaxy merger. It begins with millions of stars. It remains gravitationally bound. Over billions of years, its massive stars die, the population fades, and the system evolves dynamically. The result could be a compact old stellar system much more massive than a typical globular cluster. That would be a UCD formed as a star cluster. Other UCDs appear to have followed a very different route. They began as galaxies, then almost everything except the nucleus was removed. M60-UCD1 provides one of the strongest examples. It lies close to the giant elliptical galaxy M60, also catalogued as NGC4649 in the Virgo cluster. M60-UCD1 is extraordinarily compact. Its total stellar mass is on the order of 100 million solar masses, and an enormous fraction of that mass lies within a radius of only a few dozen light-years. NASA estimates that its central stellar density is thousands of times greater than the density around the Sun. For a while, its compactness alone made it interesting. Then astronomers measured what was happening at the centre. M60-UCD1 contains a massive black hole. The black hole has a mass of roughly 20 million suns in modern dynamical measurements, with early observations already showing that it represented an unusually large fraction of the entire system. A black hole that large is difficult to explain if M60-UCD1 formed as an ordinary star cluster. Massive central black holes are associated with galaxies. The simplest interpretation is that M60-UCD1 used to be much larger. Picture a normal small galaxy containing a dense stellar nucleus and a central black hole. It approaches M60. Tidal forces from the giant galaxy begin removing the outer stars. The loosely bound outskirts are stripped first. The satellite loses more material on later passages. Its size decreases. Its total stellar mass falls enormously. The dense nucleus survives because its stars are held much more tightly together. Eventually, what remains looks like a tiny galaxy, consisting almost entirely of the original nucleus. The black hole did not become unusually large. The galaxy around it became unusually small. This explains why the black hole represents such a high fraction of the remaining mass. It is a galactic fossil after most of the galaxy has been removed. M60-UCD1 therefore links directly back to nuclear star clusters. Take a galaxy with a nuclear cluster. Strip away the rest of the galaxy. The nucleus becomes an isolated compact stellar system. Observe it billions of years later without knowing its history, and you might mistake it for an enormous globular cluster. A black hole can reveal what happened. Fornax UCD3 offers another example. UCD3 belongs to the Fornax galaxy cluster and was among the systems that helped establish the UCD class. It is unusually large for a UCD, with a half-light radius approaching 90 parsecs, and contains an extended faint envelope around its compact inner regions. Detailed observations have also revealed a central black hole of roughly 3 million solar masses. That black hole accounts for several percent of the system's stellar mass. Its presence again favours an origin involving a stripped galactic nucleus. The stars in UCD3 are relatively metal-rich, another clue that the object may once have occupied the centre of a larger stellar system capable of sustained chemical enrichment. Not every UCD contains a detected black hole, and even among those without one, absence of evidence is not necessarily evidence of absence. At distances of tens of millions of light-years, measuring stellar motions across a tiny object requires extremely high spatial resolution. A smaller black hole could simply be difficult to detect. Still, the black holes found in systems such as M60-UCD1 and Fornax UCD3 changed the debate. They demonstrated that at least some UCDs are stripped galaxies. That does not mean all UCDs are. At lower masses, the properties of UCDs overlap smoothly with massive globular clusters. There may be no meaningful physical line separating the most massive clusters from the least massive UCDs. Some formed as clusters, some formed as galactic nuclei. The two populations occupy the same region of size and luminosity. This makes the word galaxy surprisingly difficult to define. A traditional galaxy is a gravitationally bound stellar system embedded in its own dark matter halo. A star cluster is a gravitationally bound stellar system without a dominant independent dark matter halo. That sounds neat until tidal stripping enters the picture. If a galaxy loses nearly all of its dark matter and outer stars, leaving only its nucleus, is the remaining object still a galaxy? Historically, yes. Structurally, it may now resemble a star cluster. The universe does not care whether the noun makes us uncomfortable. Omega Centauri may belong somewhere in this discussion as well. We met it earlier as the most massive globular cluster associated with the Milky Way. Its multiple stellar populations, spread in chemical abundance, enormous mass, and complicated history have long supported the suggestion that it may be the stripped nucleus of a dwarf galaxy. If so, Omega Centauri and objects such as M60-UCD1 would represent related outcomes at different masses. One is traditionally called a globular cluster. One is called an ultra-compact dwarf. Both may be the dense survivors of galaxies that lost their outer structures. M54 NGC6715 provides an even clearer illustration of the connection. It lies at the centre of the Sagittarius dwarf spheroidal galaxy, which is currently being disrupted by the Milky Way. M54 is generally classified as a globular cluster, but its central location inside Sagittarius shows how a massive cluster and a galactic nucleus can overlap conceptually. Continue stripping Sagittarius for long enough, and the surviving central stellar system may eventually resemble something we would classify differently if we encountered it without knowing its history. This is why the strangest stellar gatherings are so valuable. They fill the gaps between the categories. Extended clusters show that globular-like populations do not have to be compact. Faint fuzzies show that old disk clusters can remain large and diffuse for billions of years. Ultra-compact dwarfs show that enormous star clusters and stripped galactic nuclei can become nearly indistinguishable. Nuclear clusters show how those stripped nuclei may have begun. Globular clusters such as Omega Centauri show that some objects classified traditionally as clusters may carry evidence of more complicated origins. The boundaries are not failures of astronomy, they reflect how stellar systems evolve. An object can begin in one category and finish looking like another. A young, massive cluster can age into a globular-like system. A dwarf galaxy can lose its outer stars and become a UCD. A nuclear star cluster can survive after its host is stripped. An open cluster can expand into tidal tails. An association can lose its recognizable structure and become a moving population. A compact object can become extended as its internal dynamics and external tidal environment change. The label we give a stellar system today describes one moment in a much longer history. To understand the system properly, we have to ask where its stars came from, how tightly they were originally bound, what gravitational environment they lived in, how much mass they lost, whether their host galaxy changed around them, and how long the system has had to evolve. Once we ask those questions, the strange objects stop looking like exceptions. They begin to look like outcomes. EC4 may preserve a cluster carried into Andromeda with a disrupted satellite. The faint fuzzies of NGC1023 may be survivors from disk cluster populations that endured for 7 to 9 billion years. M60-UCD1 appears to preserve the nucleus and black hole of a galaxy that was once vastly larger. Fornax U-CD3 carries another massive black hole inside an object compact enough to fit between familiar definitions. Each one is evidence that the present shape of a stellar gathering is only part of its identity. That leaves one final problem. We have spent all this time sorting clusters by what they look like now. Embedded, open, globular, associated, dispersing, massive, nuclear, extended, ultra-compact. But no star cluster remains exactly what it was when it formed. Stars lose mass, massive members die, gas leaves, gravity rearranges the survivors, galaxies pulled from the outside, clusters merge, expand, evaporate, migrate, and sometimes disappear completely. To understand why all these forms exist, the categories have to be set aside for a moment. We have to follow the cluster itself from the cloud that creates it to whatever remains after the cluster is gone. Every star cluster begins with gas. Before there is a Pleiades, a 47 Tucanae, a Westerlund one, or an object strange enough to make astronomers debate whether it is technically a galaxy, there is cold interstellar material being pulled together by gravity. The details vary enormously. Some clouds contain enough material to form a few dozen stars. Others belong to giant star-forming complexes capable of producing thousands of stars in several related groups. During galaxy mergers and starbursts, enormous quantities of gas can become compressed and produce young, massive clusters containing hundreds of thousands of solar masses. Near galactic centers, high pressures and strong gravitational fields create still different conditions, but the basic requirement is the same. Some region of gas must become dense enough that gravity wins. The cloud contracts, dense structures develop, filaments feed material into compact cores. Those cores fragment, protostars form, disks appear around them, jets emerge. Some stars grow rapidly, others remain small. Binary and multiple systems develop. Before the stars have finished forming, the first recognizable stellar group already exists. That is the embedded stage we began with. At this point, the cluster's future is uncertain. The stars contribute gravity, but so does the remaining gas. Some stellar systems may already be strongly bound. Others are only temporary concentrations inside a larger star-forming region. Massive stars start changing the environment almost immediately. Ultraviolet radiation heats and ionizes nearby gas. Stellar winds push material outward. Low-mass stars produce jets and outflows. The cloud that created the cluster begins to disappear. This first period is dangerous for a young stellar system because losing gas changes its gravitational structure. Imagine a collection of stars moving inside a potential created partly by stars and partly by gas. Remove a large fraction of the gas quickly, and the stars keep moving at roughly the speeds they had before. The gravitational field is now weaker. Some stars find themselves moving too quickly to remain bound. The group expands, members escape. If the system began only weakly bound, much of it can disperse in a relatively short time. Older observations of young cluster populations led astronomers to use the phrase infant mortality for the rapid disappearance of many young stellar groups. The terminology is dramatic, although nobody has yet proposed a tiny memorial service for an unbound cluster. The important idea is that forming stars together does not guarantee that they will remain together. Many young groups probably never become long-lived clusters. Some disperse within tens of millions of years. Their massive B-type stars can still be alive when the original cluster structure has already vanished. The stars remain visible, but the cluster does not. Other systems survive the clearing of their gas. They emerge as exposed open clusters. The Pleiades is one example. Its original molecular cloud is gone. The stars remain related by age, motion, and gravity. At around 100 million years old, the Pleiades has already survived far longer than many young stellar groups. That does not mean it is permanent. Internal gravitational encounters constantly redistribute energy. One star passes another, and both trajectories change slightly. Repeat that across hundreds or thousands of stars for millions of years, and the cluster's structure evolves. More massive stars tend to move inward. Lower mass stars become more common in the outer regions. Some stars acquire enough energy to escape. This slow leakage is often called evaporation. The cluster is not literally evaporating in the way water leaves a cup. The phrase describes stars gradually escaping through gravitational interactions. The surrounding galaxy accelerates the process. A cluster moving through the Milky Way experiences a tidal field. The gravitational pull on one side of the cluster differs slightly from the pull on the other side. Stars in the outskirts can cross the boundary, where the cluster's gravity is no longer strong enough to retain them. They escape into leading and trailing tidal structures. Passing molecular clouds can disturb the cluster much more strongly. A large cloud does not need to collide directly with every star. Its gravitational field is enough. The encounter can change stellar velocities, expand the cluster, and remove members. Disk crossings and passages near massive galactic structures create additional disturbances. Each event removes a little of the original system. The Hyades shows this happening nearby. The familiar central cluster is only part of its true population. Gaia observations have traced former members into enormous tidal tails extending far beyond the visible V-shaped group in Taurus. Those tails contain stars that still preserve enough common motion to reveal where they came from. The cluster is gradually becoming part of the Milky Way's disk. That is the normal fate of many open clusters. They do not explode. They fade into the background population. A member escapes today. Another escapes. Thousands of years later, the cluster expands. Its density decreases. More stars become vulnerable to the galactic tidal field. Eventually, the surviving central concentration is too weak to remain recognizable. At that point, the stellar family has not stopped existing biologically, if we can use that word for stars. The stars are still there. Their organization has ended. A young association reaches that condition much earlier because the large-scale population may never have been gravitationally bound. Skosen is already spread across a large region. Orion OB1 contains several distinct populations with different ages and motions. Taurus Auriga follows the structure of its parent molecular clouds rather than forming one compact spherical cluster. These systems dissolve into the galactic field almost as a continuation of their formation. Moving groups preserve the relationship for longer. Beta Pictoris contains stars now spread through the solar neighbourhood but still connected through motion and age. Eventually, even that connection becomes difficult to recover. Galactic rotation changes orbital phases. Spiral structure perturbs trajectories. Molecular clouds pass nearby. Stars migrate through the disk. A population that was clearly related after 20 million years may be impossible to identify confidently after several billion. The Sun's original siblings demonstrate the problem. The Sun almost certainly formed alongside other stars about 4.6 billion years ago. Where those stars are now is uncertain. Some may be elsewhere in the Milky Way at distances of thousands of light years. Their chemistry may still resemble the Sun's. Their ages may match. Their orbits have had billions of years to diverge. The original group has become galactic memory rather than a visible structure. Massive clusters follow the same physical rules, but gravity gives them more time. Take a system such as Westerlund 1. It begins with tens of thousands of solar masses packed into a compact region. Its massive stars evolve rapidly. Within only a few million years, the highest mass stars lose large amounts of matter through winds. Some become Wolf-Rayet stars. Some expand into supergiants. Some collapse and leave neutron stars or black holes. Supernovae remove additional mass. This means a massive cluster changes gravitationally even if not one star escapes through an ordinary encounter. The stars themselves lose mass. The cluster's total mass decreases. Its gravitational field weakens. The system can expand. Some members become unbound. The earliest evolution of a massive cluster is therefore heavily influenced by stellar evolution. Later, internal dynamics become increasingly important. Mass segregation concentrates heavy stars and remnants toward the center. Binary systems exchange energy with passing stars. Black holes interact with one another. Some compact objects are ejected, others remain. The cluster loses low-mass stars from its outskirts. Its stellar mass function changes. A 10 billion-year-old cluster is not simply a young cluster whose stars have aged. Its membership has been edited continuously. The stars easiest to remove have often been removed. The central population has been rearranged. Binary systems have changed. Remnants have accumulated. The cluster may contain only a fraction of the mass with which it began. This makes ancient globular clusters especially interesting. When we observe Messier 13 or 47 Tucanae, we are not seeing a preserved sample placed into storage 12 billion years ago. We are seeing survivors after billions of years of stellar evolution and gravitational processing, the massive stars disappeared early. Many lower mass stars escaped, some binaries merged, white dwarfs formed, neutron stars appeared, black holes were created. The cluster orbited through its host galaxy repeatedly. Its structure responded to every one of those events, yet the system remained recognizable. That survival tells us that globular clusters began with significant gravitational binding. Some may also have been substantially more massive when they formed. Exactly how massive is still an important question, particularly because globular clusters contain multiple stellar populations with unusual chemical abundance patterns. To explain those patterns, some formation models require early clusters to have retained or reacquired gas, produced multiple generations, or lost a large fraction of their original stars. The details remain debated. What is clear is that ancient globulars are not dynamically frozen. Some are slowly expanding, some have dense collapsed cores, some are losing stars rapidly, some sit on orbits that expose them repeatedly to strong tidal forces. Palomar 5 shows a globular cluster close to the destructive end of this process. Its present cluster contains only part of the original stellar population. Long tidal tails extend along its orbit. Earlier studies found more stars in the visible tails than in the remaining central cluster. The Milky Way is pulling the system apart. At some point, Palomar 5 will no longer exist as a compact cluster. Its stars will continue around the galaxy as a stream. GD1 shows the next stage. Its likely globular cluster progenitor is no longer visible. Only the narrow stellar stream remains. Wait longer, and even that stream becomes harder to distinguish. Its stars spread around the orbit. Perturbations alter their velocities. The stream broadens. Eventually, the debris becomes part of the stellar halo. The final remains of the cluster are not a compact object at all. They are stars whose common history can only be reconstructed statistically. That is one way a cluster dies. Another is migration. A massive cluster orbiting inside a galaxy can lose orbital energy through dynamical friction. Instead of being destroyed in place, it gradually spirals toward the center. As it moves inward, tidal forces strip away outer stars. The dense core may survive long enough to reach the nucleus. There, its stars join other populations. Repeat the process with several clusters, and a nuclear star cluster can grow. The cluster still disappears as an independent system. Its stars become part of something larger. This makes destruction a slightly misleading word. A cluster can dissolve. It can be stripped. It can merge with another cluster. It can be incorporated into a galactic nucleus. Its stars can be scattered through a halo. The structure ends, but the material continues participating in galactic evolution. A galaxy is constantly recycling the remains of stellar systems. Stars that escape open clusters join the disk. Stars stripped from globular clusters join the halo. Gas returned by aging stars becomes part of the interstellar medium. Supernovae enrich that gas with heavy elements. Later, molecular clouds form from material containing products of previous generations. New clusters appear. The process does not produce an exact cycle, because the conditions change. Each generation forms in gas with a different chemical history. The galaxy itself grows and evolves. Its spiral structure changes. Satellite galaxies arrive, mergers occur, gas is consumed, expelled, or accreted. Still, there is continuity. The oxygen in a young star may have been manufactured inside an older star that belonged to a cluster long since dissolved. The iron in a planet may come partly from stellar explosions that occurred before its host star formed. The cluster disappears, but its material does not leave the story. This becomes even more obvious when galaxies merge. The antennae galaxies currently contain large populations of young, massive clusters produced during their interaction. Many of those clusters will not survive for billions of years. Some will dissolve. Their stars will become part of the remnant galaxy formed by the merger. a small fraction of the most massive and compact clusters may endure. Far in the future, those survivors could resemble old massive clusters, while the vast majority of their siblings have blended into the galaxy around them. If we looked only at the survivors, we might underestimate how many clusters originally formed. This is exactly the problem we face with ancient globular clusters. The Milky Way contains roughly 150 known globular clusters today. That does not mean it formed or acquired only 150. Some have already been destroyed. Streams such as GD1 are direct evidence. Other destroyed clusters have been mixed so thoroughly into the halo that their original boundaries are gone. Chemical abundance patterns and orbital structure may still identify remnants of some. Others are probably unrecoverable. The present cluster population is a survivor sample. That introduces a bias into almost everything we infer about cluster formation. The clusters easiest to destroy are no longer available for observation. The ones we study after 10 billion years are those that had the right combinations of mass, density, orbit, and environment to remain intact. Imagine trying to determine what houses were built in a city 500 years ago by examining only the buildings still standing. You would learn a great deal about durable construction. You might get a very poor estimate of the average house. Globular clusters create a similar problem on a much longer time scale. Their survival tells us something about their initial conditions, but the missing population matters too. Extended clusters add another piece. A diffuse cluster such as EC4 can survive in a weak tidal environment, but might be destroyed quickly if placed near a galactic center. Faint fuzzies can survive for billions of years on favorable disk orbits despite their large sizes. Ultra-compact systems survive extremely well because of their high densities. Environment determines which structures remain. The same cluster can have different lifetimes depending on where it orbits. Place it far into a halo and the tidal field is weak. Move it into the inner disk and molecular cloud encounters become more frequent. Bring it close to a massive galactic nucleus, and tidal forces can remove stars rapidly. There is no universal clock that says an open cluster lives this long or a globular cluster lives that long. Lifetime emerges from the interaction between the cluster and its surroundings. Internal structure matters just as much. A compact cluster holds stars more tightly than a diffuse one of the same mass. A more massive cluster generally has a deeper gravitational potential. Binary stars can provide energy that delays core collapse. Black hole populations can heat central regions and change expansion rates. Stellar mass loss alters the gravitational field. Different initial mass distributions produce different evolutionary paths. Even two clusters born with the same age and total mass can end up looking different after several billion years. This makes classification useful but incomplete. We began with embedded clusters because they tell us where stellar groups come from. Open clusters showed what happens when some young systems survive gas removal but remain relatively loose. Globular clusters showed what strong gravitational binding can preserve over cosmic time. Associations showed that shared birth does not require permanent binding. Moving groups and streams showed how relationships persist after obvious structure disappears. Young massive clusters showed the environments capable of producing long-lived compact systems. Nuclear star clusters showed how repeated star formation and inward migration can build stellar systems at galactic centers. Extended clusters, faint fuzzies, and UCDs showed that those histories can produce objects between the familiar categories. Taken together, these are not 10 isolated kinds of object. They're outcomes of the same basic ingredients used in different amounts: gas, gravity, stars, time, and a galaxy around them. The amount of gas determines how much stellar mass may form. The efficiency of star formation helps determine how strongly the newborn system is bound. The density influences how frequently stars interact. The stellar mass distribution controls how quickly mass is returned through winds and supernovae. The galactic orbit controls tidal stress. The host galaxy determines whether the cluster experiences molecular clouds, strong central gravity, or a relatively quiet halo. time allows all of these processes to accumulate. A cluster can therefore change category without any dramatic boundary crossing. An embedded cluster becomes exposed, an exposed cluster expands. A young massive cluster ages into something globular-like. A globular cluster loses mass and develops a stream. A nuclear cluster becomes an ultra-compact dwarf after its galaxy is stripped. A stellar association becomes a moving group. A moving group eventually becomes indistinguishable from field stars. At each point, an astronomer arriving with a telescope would classify what exists at that moment. The full history is longer than the label. This is why stellar clusters are so useful for understanding galaxies. They preserve information that individual stars can lose through mixing. A group of stars with similar age and chemistry can reveal a shared formation event. An ancient globular cluster can preserve conditions from the early Milky Way. A tidal stream shows where a cluster has travelled. An extended halo cluster can indicate an accreted satellite. A UCD can preserve the nucleus of a galaxy destroyed billions of years ago. A young cluster can reveal how quickly disks disappear around newborn stars. The cluster is both an object and a record. Even after the object disappears, part of the record can remain. Gaia has made that particularly clear in the Milky Way. Clusters once thought to end at a small visible boundary are now surrounded by extended populations of escaped stars. The Hyades has tidal tails stretching across enormous distances. Other nearby clusters show related features. What once looked like a neat collection of stars now appears more like the dense centre of a much larger process of dispersal. Future surveys will push this farther. Better stellar motions will reveal weaker tidal features. Large spectroscopic surveys will measure chemical abundances for millions of stars. Infrared telescopes will find clusters hidden behind dust. James Webb observations are already examining compact star-forming systems in galaxies seen at much earlier cosmic times. Researchers can begin connecting newborn clusters in the distant universe with the ancient survivors around galaxies today. That connection is still incomplete. We do not yet have one simple model explaining how every globular cluster formed. We do not know exactly which young massive clusters will survive for 10 billion years. We cannot reconstruct every destroyed cluster that contributed stars to the Milky Way. The original nursery of the Sun remains uncertain. The formation routes of all UCDs are not identical. The detailed histories of nuclear clusters vary from galaxy to galaxy. Those uncertainties are not missing pieces that make the subject useless. They are the reason clusters remain active areas of research. A star cluster is one of the few places where astronomers can study stellar birth, stellar evolution, gravity, galactic dynamics, chemical enrichment, black holes, planet formation, and galaxy assembly using the same population of stars. That is an impressive amount of responsibility for something that sometimes looks through binoculars like a smudge. Perhaps that is also a useful way to look at the night sky. The stars do not begin as isolated points placed one by one into darkness. Most are born around other stars. They spend their earliest years in environments shaped by neighbours. Some remain beside those neighbours for billions of years. Others separate quickly. Some cluster families can still be recognised easily. Others have been spread across entire galaxies. The Sun belongs to the second group. Its birthplace is gone. Its siblings have wandered. The night sky around us is filled with stars whose original families may be just as dispersed. A few of those families remain obvious. The Pleiades still travels together. The Hyades is slowly coming apart. Globular clusters still orbit the Milky Way carrying ancient populations. Streams mark the paths of systems already destroyed. Near galactic centres, stellar generations continue gathering into nuclear clusters. Far outside the Milky Way, young massive clusters are forming in galaxies that may look very different by the time those clusters become old. None of these systems needs to last forever to matter. A cluster can survive 10 million years and influence the formation of planets. It can survive 10 billion and preserve information about the early universe. It can dissolve and still contribute stars to a galactic disk. It can be stripped and leave a stream. It can sink into a nucleus. It can survive the destruction of an entire galaxy and remain behind as a compact stellar fossil. Its lifetime is only one part of its role. And here we are, back among individual points of light. Perhaps the room is darker than it was when we started. Perhaps you're still listening closely. Perhaps you have reached that pleasantly uncertain stage where the words are becoming a little harder to follow, and the distinction between an open cluster and an ultra-compact dwarf is beginning to feel like tomorrow's problem. That is perfectly acceptable. Before we leave these stellar families behind, you might think again about the sky above wherever you are tonight. Somewhere beyond the roof, the clouds, the streetlights, or the daylight on the other side of the planet, stars are forming inside dusty clusters. Elsewhere, open clusters are losing members. Associations are spreading. Globular clusters are crossing galactic halos. Tidal streams are stretching farther along their orbits. Massive stars inside young clusters are ending their lives. Nuclear clusters are collecting new populations near galactic centres. None of it requires the stars to know that they belong to a group. Gravity is enough. And if this slow journey through the different kinds of star clusters has helped you relax, given you something interesting to think about, or carried you a little closer to sleep, you can leave the video a like and subscribe to Science for Sleep. It helps this quiet corner reach other people who might also enjoy learning about several million stars without needing to meet any of them personally. For now, there is nothing more you need to keep track of. Not the catalogue numbers, not the distances, not which clusters survive and which dissolve. The stars will continue moving whether we follow them or not. So let the Pleiades drift through Taurus. Let 47 Tucanae keep its crowded orbit. Let Palomar 5 lose another star into its stream. Let the hidden clusters behind galactic dust continue forming new suns. And wherever you are listening from, let your own part of the galaxy carry on quietly around you. Sleep well, fellow traveller.